So today, what I'm going to do, since I have the privilege or not of knowingly the longest, and except probably for Susan Edwards that must be listening, I think that maybe she met him a little bit earlier than me. I met him once, first time in Patras, right? And the first thing he ever told me, why haven't you published your thesis? So that was the first thing he ever told me, and that's where I met him. Okay, so, but because I have this privilege, what I'm going to give today is like a biased walk through history of accretion in young stellar objects with emphasis in Lee's role. And I will leave the recent work to others because, you know. Okay, so Titori stars, they were discovered by Joy in 1945, these funny objects with a bunch of emission lines in dark clouds. And the 50s, George Hervik in California, Guillermo Haro in Mexico, they spent the time just studying these objects, and they were actually, they're summarized by Hervik in 62 in this paper. But I really like this paper, The Nature of the Objects of Joy, by the Stroms and Reagan. And the thing is that, yeah, these objects have brought us a lot of joy through all this year, and also a lot of pain. And in particular to Lee, so much so that he even published a book about it. Okay, so, but let me go back and start from the beginning. So back in 1974, Lyndon Bennett Pringle published this paper, right? And in which they had like a self-similar solution for the disk, you know, viscous evolution, and they actually explain everything. You see, this is the start, this is wavelength increases that way, wrong way. Of course, that's your teacher. So you got like the star, you got like the UV excess that we see. You even have the disk. Everything was on it at that time. And well, the slope was lambda to the -4/3, but okay. So, but the thing is, at that time, you know, 74 in the 70s, I was a grad student at Berkeley, and I was studying with Cui and, you know, Cohen and stuff, Titori stars, and we completely dismissed us. So instead, we actually were working in the chromospheric hypothesis for Titori stars. And that all started because Hervik proposed it. What he said is that we have like the sun, the Titoris would be like the sun, active stars, but with a chromosphere that started their temperature rise, started sooner, deeper into the star. And so there were a lot of works on this amplified solar chromosphere hypothesis. And of course, at the end of the 70s, it was supported by the first observations of the IU satellite that they had this line that looked like the transition region in the sun, right? With all these highly ionized metal lines. And at the same time, right, they started like this current of people trying to explain the blue shifted absorption that sometimes was seen in some things like H-alpha. And that's where like the first Harman and McGregor like put their model into. They had done that for cool stars. They put it into Titori stars. And then Lee started working with Susan Edwards. And then Antonella Nata with Giovanardi, they started working on these too. So, and the winds too. So the idea is that you had the wind that explained, could explain like the blue shifted absorption, and also like the flux that you needed in H-alpha. The chromosphere, and I tell you, I tried very hard. The chromosphere or anything small like a boundary layer cannot explain the emission that you see in H-alpha. But the idea here, there was also some rumors. There had to be some kind of disks, flattened structures, because there was no correlation between the near infrared and the UV and the extinction. So already in Cohen and Cui said, well, there has to be something like that. Okay. But at the same time, there were these mysterious objects, which were the YY Orionis variables. And they were first mentioned by Walker in 1972. And what you could see is like this red-shifted absorption component, like the inverse P-Cygni profiles. And then there was a lot of work in Heidelberg, Appenzeller, Wolf, Klober too, there was a student there on these objects. And the main idea here was that these were the protostars. These were the stars where you still had them fall onto the surface. We didn't bother too much the fact that we could see the stars, but that's another story. So, but the main idea is that there was spherical symmetry and those were like the protostars. But then Susan Edwards, back in Hawaii, she was a student, she was getting all this spectrum, and she was one of the ones mentioning that sometimes in the same star, you could see some blue shifted absorption and in other lines, red shifted absorption. That's funny, right? And so she had high resolution, 3,000, 4,000 instrument. But then I remember, this is something I remember. So legend goes that one night, Lee was in Mount Hopkins observing his active stars, doing transition regions, main sequence, red giant, that kind of weird things. And then he had some free time, as every observer knows that you always have free time. And then he decided that he was going to take some spectra of some Titori stars. And so he got this beautiful spectra with resolution of 30,000. First time ever I had seen that. And I honestly remember 4 years ago looking at this spectrum of the F tau, and that you could see in the same line, not even in the same star, but in the same line, you could see both blue shifted and red shifted absorption. And so this seems silly right now, right? But the thing is, there was like the concern, how can you have both inflow and outflow at the same time, right? Seems silly now, I understand. But the thing is that people were just thinking spherical symmetry, right? And even like Lee here, says that motions were probably some radial outflow, but there were some funny things that were explaining those red-shifted absorption, but mostly was radial, spherical symmetry. Okay, so, but then at the same time, we got iris, right? The first observations in the infrared, and then it was obvious that there was all this excess in the mid-far infrared, right? Of discs, right? We had indeed these flattened structures. And so, and these are Rusinski, the first paper, the classical paper of at the time, the iris observations, wow, discs. And if I look, this is a TW hydride, you can still already see that this is a transitional disc, but that's another story. Okay, so Lindelberg and Pringle were actually rediscovered, brought over, and then said, well, these are accretion discs. And because they're accretion discs, what do you expect? What half of the accretion energy is emitted in the infrared in the disc, the other half in some kind of boundary layer, right? And that was great, except that it had a few problems. One is that the SEDs were not like that expected from an accretion disk. Lambda, if lambda is not lambda to minus 4/3. And also, of course, that cannot explain the red shifted absorption at few hundreds of kilometers per second. No way. Okay, I'll come back to this, but let's look at the SED. And then, and there was well, how can it be? Whatever, flat disc, funny discs. And then this is a very important paper, the flared disc by Kenyon and Hartman in 87. And what they proposed was that the discs were flared, right? And the discs were flared because they were filled, or the agent of heating, the most important heating agent was the star, which is natural if you think that the accretion for typical M dots, the accretion luminosity is just a 10% of the stellar luminosity. So the star is in there, heating the disk. And so you have that, they call it reprocessing, and then the radiation from the star hits the disk and then comes out reprocessed into the infrared. Right, and so that's the way it started. And actually, they put that those are different. It's called the flaring parameter these days, but it's essentially the same thing. The scale height goes like R to some power, and then they actually understood, right, that this is not just a flaring parameter, it's some natural consequence of the fact that the disk is heated. So they actually calculated a self-consistent temperature structure that produced that kind of excess, right? And they did a lot of models. They actually even, let's say, well, suppose using this prescription that was, I think, the first time that was done, and now it's been done very, very often. So just adding like the radiation flux with the viscous dissipation, and then you could see the transition from a typical Titori disk, right, with a flare disk, to something, as you increase them, though, to something that goes more and more towards an accretion, typical accretion disk. And they apply it to some stars. The fits not were that good, but they were the first ones. So it was great, right? And then, of course, this with time, this actually evolved into more sophisticated model. Paola D'Alessio, for instance, that's her model. And at that point, so this is a sketch done by Melissa McClure of the model. And then you have in here like the upper layers that are heated, right, because of the external radiation, a cool mid-plane, and then in the inner part you have like viscous dissipation, and then you have like this thing in here, which is like the radius where the dust gets sublimated. And then you have like different populations of dust, and that produces, well, okay, this is the star, but then the mid-infrared would come from this edge, this dust wall, where the dust just forms, condenses, and then the rest will be the disk, right? And just to show the degree of sophistication, this is like one of Melissa McClure's papers in which it compares disks with that are highly accretors with less settled dust, with disks that are more settled and less accreting less, and so you can see that this is trying to reproduce both optical near infrared, Spitzer data, and even Herschel data, right? So there have been a lot of development on that. Okay, so this is even a more recent application of those models, Karina Mauko, and those are older disks, the 5 and 10 million years disks in the Orion ORI 1B and 1A associations. And one interesting thing is at that age, it seems that all the disks have already developed gaps that you can see in the SEDs. Okay, so now we've done a lot of advance. We realize that we have disks, and most of the infrared emission comes from that. But let's go back to list profiles. And as I told you, list profile, the thing idea is that you had blue shifted and red shifted absorption in the same line. And people were saying, how can you have outflow and inflow at the same time? That makes no sense. And how can you actually do it? Well, just drop spherical symmetry, or remember that angular momentum is conserved, right? And if you remember that, then you know that you're going to have disks, right? Because the collapse of a cloud with this, with some angular momentum, some rotation, forms a disk. And so then it developed like to the magnetospheric accretion model. This is the well-known picture of the, you already saw it twice yesterday. And this is the paradigm that is more accepted for accretion in Titori stars these days. So what you have a disk, right? Where matter is paralleling, accreting, right? At some point in the disk, you get like the sublimation, the dust sublimation. That's the inner dust wall that produces all the infrared. But it's just that inside that, the disk continues inwards, but it's just pure gas that doesn't have much absorption or emission, but it's pure gas, continues inwards. And at some point, right, at a few stellar radii, it actually, the disk is truncated by the stellar magnetic field. After that, matter continues accreting, but actually does it along the magnetic field lines, following the magnetic field lines. In this case, we usually assume it's dipolar, and in large scale, it seems to be dipolar, at least in T-Tauri stars. Okay, so it falls into the star, free falls into the star, pressure zero, so with approximation, falls into the star, and when it hits into the star, I like what Peter said, it shocks the star, right? Forms a shock in the stellar surface and emerges into, slows down, all the kinetic energy goes into thermal energy, and depending where it falls, is most of the accretion energy is dissipated in emission in this accretion shock. But, and then this flows in here are pretty hot. That's where the emission lines form. And as you can see, are emission lines that are mostly centrally at zero velocities, because most of the bulk of the emission is going to come from the regions from which just lifted from the disk, right? And then what you have is like two things, right? You got like the inner disk winds, right? And these winds are actually absorbing against the magnetosphere and produce the absorption component. But also, because you have that, you have like, if you have the line of sight in here going through this line, right? You have redshifted absorption components at very high velocities, because this is essentially free fall. This is material that is falling into the star, into the shock, and is absorbing absorption into the shock. And there you have infall, outflow at the same time, together with a absorption component coming from here, an emission component coming from here, and just the line. Right? And it's just because you just had, you know, conservation of energy and of momentum. Okay. Now, this model proliferated. I mean, has been applied many times. The first more complete applications were, well, in the 90s. These are examples of the paper by James Mosserol. The idea, when you have a very high accretor, like DR tau, for instance, H alpha has an additional contribution from the wind. And then that's why the profile looks essentially P Cygni, because it's the outer wind. But then in other stars that are not such high accretors, you see that that's a typical T-Tauri profile. And then you can also see it in other lines, right? So, and this is, I think, is the only way, I think, or people can say a safe way to get them done for several types, some types of objects, for instance, for very low mass stars and brown dwarfs. There are few that are bright enough that you can see the UV excess, but there are very few. So most of the time you just model the H alpha line, and then you can get the M dot. Another application is, for instance, for the very embedded objects, the class 1, the true protostars, the one that still have outflow, infall, and those you cannot see in the optical. But then when you actually do modeling, what you see is like the accretion luminosity is much lower than the stellar luminosity, the volumetric luminosity, which it was can be used to explain, say, the luminosity problem, but or created the luminosity problem, but that's another story. Okay, so it's been applied multiple times, and most recently, this is from Tanagusta Nasibodis, a former student of mine, and what he did in here, he modeled PDS 70. PDS 70 is a very low accretor, 10 to the minus 10, and you see that the line has a chromospheric contribution, which is very important, but then it has broad winds and the redshifted absorption component, given like the M dot. And moreover, this is the object that has a disk that has two planets, and the planets have the little disks, and they are even accreting, and you can see H alpha here. These are Miriam's most recent ALMA image of the object. And so what Atom did, and Asibo did, he actually modeled the H alpha flux with magnetospheres, right? And what he could see is that you could very well explain the fluxes. These are like the observations with mass accretion rates onto the planet of 10 to the minus 8, but now Jupiter masses per year, which is 10 to the minus 11, right? 10 to the solar masses per year. Okay, and the most recent application is like this is a recent paper in which the idea was trying to explain the variability in the blue, in the U band and in the optical, and there was some shift in the maximum. And the idea is that the column, the actual accretion column, is nothing actually perfectly beautiful, but it's something that has some structure as proposed by, sorry, oops, no. Yeah, sorry. As proposed by, those are the models of Romanova. And the idea is that the U comes from the more active part, the denser part of the column that hides behind the star first. And then you can see like the visual part, or the less dense parts of the column, they hide later. And the idea is that the geometry of the chromosphere can be constrained with this magnetospheric model. This is a recent paper by Spagliati in Nature. And of course, there have been plenty of other applications. Gustavo Lima and Silvia Alencar, they actually put it in this plus magnetosphere, and they could create like the blue shifted absorption self-consistently. And right now I have several students doing applications of that, the same simultaneous modelings of all the, the Balmer, the Paschen, the Bracken lines of in X-shooter spectra, or like trying to understand the extinction of very heavily veiled objects in which you don't have way to compare, by using these models, and by Jesus Diaz, that's Maria Jose Colmenares, and then the evolution of magnetospheric flows, observing, characterizing the magnetospheric flows in associations of different ages by Nayara Patiño, and then my new student, Marbeli Micolta, the heavy element content of the disk by looking at the lines in the flows. Okay, so this is all done. We've done a lot of things. Okay, so let's go back in time, and let's go to another type of objects, the FU Orionis objects. Okay, so back in 75, George Herwig gave the Russell lecture in the AAS, and he presented these objects in which they have like increase in a few months, the magnitude can increase by 7 magnitudes, 7 magnitudes, and he gave the talk, and in short, no convincing explanation of FU Orionis phenomenon was available. And he said something about, he thought that it was a star, but something was happening to the star, that some kind of like all of a sudden the dust cloud went around, it disappeared. It wasn't clear what it was. Well, Lee was in, maybe I don't know if it was your first AAS, but he was wandering around. He went to the talk, and then he actually got all excited about it. He was still studying transition, active stars, but he got interested. So time went on, and then another time he was wandering around, now in the CFA. In my mind, he's a wanderer, So, and he actually went to a talk by Scott Kenyon, who used to work in cataclysmic variables, and then he saw like the instabilities on disks in cataclysmic variables, and how they magnitude increased so much. And so I said, well, let's put the hypothesis that they are actually highly accreting disks. That these, the F Orionis are things that are accreting very heavily. And what we are seeing is the disk itself. Of course, Herwig did not like that. I did not like it at all. Okay, so the idea was then that you have to prove that they were disks, right? So emission from the disk implied that you have a temperature dependent on time, T of R, right? Not just one single temperature, a bunch of temperatures, right? And that one of the implications is that the spectral type would have to change with wavelength, right? The other had that the lines had to be double peak because it's the spectrum of a ring. And also that if it was a disk, it had Keplerian velocity. So the velocity had to decrease as the wavelength increased. And finally, of course, if it's a pure accretion disk, the LCD has to be like lambda to the minus 4/3. So they actually set into this quest to prove that they were disks. And this is from the annual review. This is from the annual review. The idea here is that these are like the emission of different annuli in a disk of m dot of 10 to the minus 4 or something like that. And then you can see what I have, these numbers are like the radius on the disk and the effective temperature. So of course, the further out you are, the lower is the temperature. But then when you look at the optically here, you're actually looking at these lines, at these regions, right? Which are the optical regions. Okay, if you look further out, how much I have? Okay. So if I have in here, if I look further out, I'm seeing things that are regions that are cooler and we have molecular bands. And indeed, when I look at, F Orionis, I can see that in the optical, it looks like a G star. If I actually look in the near infrared, I see the molecular bands. Perfect. Fine. The lines are double lines. Yes, great. And they are double line profiles. And that was known. But then what they did is they took up the spectrum in the optical and the near infrared, and these are cross correlations. And then from the width of the cross correlation peak, you can measure the velocity, and you can see that in the optical, it's wider than it is in the near infrared. So check. So those things check. Now, Herwig and Petrov, they were pretty upset. They said, but the strong lines are single lines. How can it be? But it's a wind. And you see, if it's a wind from the surface of the disk, it starts slowly and then the velocity increases. So you have a weak line that forms in here. It will have double lines because it's rotation dominated. But if you have a strong line that forms higher up in the disk, right, where the optical depth is one up there, right, where the rotational velocity, where the wind velocity is so much higher than the rotational velocity, it will be just a blue shifted line. And that was the prediction, and that was the observation, right? So check. And finally, of course, the SED, the steady disk, and it actually fits very well in here. In fact, this Suniev calls it the textbook example of accretion disks, and it's the triumph of accretion. Of course, like Shawan showing his thesis, farther out, it's not like a steady disk, but because you have the extra contribution from the cloud. And that is like what's happening, right? The idea here, physically motivated, is that you have like this imbalance between the m dot, right? The material is falling to the disk, but it's not dumped into the star at the same rate. So accumulate, eventually there are instabilities, and then thus like the accretion increases, and then of course the luminosity increases, and at that point you are only looking at the disk. So that's the idea. That must have been a great time, right? Because all these things, check, wow. So it never happens, right? So, and then of course I will listen we hear about that, luminosity problems, these instabilities, all the episodic accretions in protostars that you'll hear about. And then, of course, building the stellar mass, because the star probably gets all this mass in these episodes of high accretion, right? And then like making the birth line, which is where the stars supposedly begin. So maybe somebody will talk about that I don't know. Okay, so another line was like measuring accretion rates. And then we saw that yesterday that Cesar showed. And I remember when they came from Mount Hopkins, right? And then they said that this was, this type of profiles have been presented before, but this supposedly have the peculiarity that it was the best photometric line ever. That nobody, for an observer, that's a unique, something once in a lifetime situation, right? So what was the story? That it was the horizon, the light of the sun, and then dark, right? So something that, observers will understand what it means. Okay, so, but the thing is that they really had that, and then he applied that to accretion evolution of this. This is the 78 paper, and is revisiting of course, the self-similar solution of Linden-Bernard-Pringle applied to the torus stars, with a viscosity is proportional to R, which is consistent with the radiated this, blah, blah. And this has been very highly cited, repeated, copied, the procedure many times, right? And we'll hear more from Bing later on. He'll talk about these things, but just to show you like a mosaic, right? Of what the things that people have been applying in here. For instance, this is the original M dot versus H. Then Moserol, like including like the class 1 objects in here, the earliest ones. These are observations, and this is like the viscous evolution, starting with a disk that has 0.1 solar masses and is evolving with an alpha 10 to the minus 2. And you see that more or less follows very well. Then already Aurora Cecilia Aguilar, actually she was including more and more associations into the thing, considering it keeps, and this is like the recent review, 2016. The ages in here are isochronal ages, but there is another line of thought that we, instead of taking isochronal ages, takes what instead is taking the age of the population, puts together in populations in beans, and then takes the median. And as you can see, even in that case, the M dot really decays follow viscous evolution. So that fits very well. And of course, the alternative things were like these papers on mass accretion versus M dot correlation that we'll hear it later from Venken. And then what you see is that this was the first time when James had like the very low brown dwarf object was put together with the T-Tauri stars at the time. And then other papers follow, Antonella Nata, Hesser and Hillenbrand. Those are included like the low mass stars. And then here we included like the intermediate mass T-Tauri stars. So the correlation continued, and we already heard yesterday by Rene, like applying it to the Herbig A stars, and when you get to the B stars, supposedly the correlations break. So there have been many papers trying to understand why M dot goes like roughly like M2 square, which I don't talk in here, but just for you to know. Okay, so the other implication of this viscous evolution is that, of course, when you have like starting for a given sigma distribution, where you just let go, and of course the evolution is that mass goes into the star, right? And in order to conserve angular momentum, like Pringle said, you have to have zero mass going to infinity, right? Just to keep that. So as a result, this expand and it expands, but at a given time, the disk is not just truncated, but it's got some exponential drop. And even though like the large disks that one would expect from pure viscous evolution are not necessarily seen, but what is being seen is that the edges of the disk are this exponential, right? There is a limiting edge of the disk, and that's been observed in the SMA and with a bunch of observations of ALMA. And I won't go again, I'm gonna finish soon, but the idea is that this self-similar solution of Lingerberg and Pringle that Lee like revived and applied. Also, Nakampoto and Nakagawa did that in '94, mentioned that. But I think that Lee was the first, the one that was better known, at least in the Western Hemisphere. Unfortunately. And the idea is, and so this self-similar solution and like this standard equation for the evolution of the sigma has been used over and over and incorporated into these models of dust evolution, right? In which there are like additional terms that take into account like the interaction between the dust and the gas and dust of different sizes, and then gets like the, you know, like the drifts and all that you hear. And then, this is like some paper like in 2020, again, comparing like 1D simulations. It's always the standard one, you know, like the expanding one. And this is the most recent one in which they actually follow the heavy element content to get to the star, right? So it's been like opening gates, right? So this is like the end of my talk, but it's not the end of the story. I think that Lee has opened very venues of research. Always better, right? Always perfectible. But the idea, but he's always been in the frontier. It's essentially pioneering work. And in accretion and in other areas that we have had. And so I think that the students are collaborators, they are already shown, and they are all very thankful. So, but I want to finish with what Lee says is his most cited work in recent years, which is this, right? And already we saw it twice yesterday, we'll hear it many times. And I know that Carlo Manara, who may be listening because he talks less, Carlo Manara said that if he saw it once more, he starts screaming. So you can start screaming, Carlo. So that's it. Thank you.
Yeah, thank you very much, Neria, for that beautiful talk. And this is the first slide in my talk, so there'll be some screaming.
No, yeah. You see.
Okay, so we take some questions from the room.
Thank you for a very nice overview. Well, precisely here, so this magnetospheric accretion is an important paradigm, but it's likely not all the story, in particular because initially, I mean, as the protostar forms, very likely the disk actually connects directly to the star. And I personally convinced, for many reasons, that I would be happy to discuss with you later, that this actually is something important to understand. And I would like to know to what extent there are maybe already some observations that could point to this kind of transition between a disk connecting directly to the star and maybe, I mean, and then the emergence of this magnetospheric accretion, which occurs, by the way, only if the magnetic field is sufficiently strong to create such cavity. And there are possibly even cases for later objects where magnetic field may not be that strong, and therefore you may still connect the magnetic field, the disk to the star. So I wonder whether there are already some evidence for this type of.
So the first one, evidence for quench magnetosphere, you just have to look at the spectrum of an FURI object. You see, FURI, for instance, when you look at H alpha, doesn't have any emission. What it has is a very deep red, blue shifted absorption. You know, like a P Cygni, but it's just absorption because the wind is not that hot, right? So just look at the spectrum of any FU, like this FURI object. In between, there are some that, you know, maybe quench, but we still have the exact transition is difficult because I don't think we've seen it. Right, we have not, many of the FU Orionis objects are embedded and so therefore cannot be seen in the optical. So it would be good to be able to see them in the optical, but the well-known objects, right, if I, correct me if I'm wrongly, but the well-known FURI objects, they all have like this feature. In principle, they should not have, they don't have chromospherics because, you know, the idea is that this quench. Of course, there are consequences of this transition, right? In the boundary layer, maybe the star has swollen because of all the infall. So, and the boundary layer may be more extended. You can see some of the papers of Liz on that. But essentially, yes, that is known. Now, the other question was, think that like older. Okay, so most of the measurements of magnetic fields in T-Tauri star, like Donati, and also that they measure, they tend to have a kilogauss magnetic fields. Like of course, they have the very convoluted structure, right? And so, but they tend to have like a standard dipolar-like geometry. Not spherically symmetric, but extended, which is like kilogauss. And if you take the standard, you have kilogauss and then m dots typical of 10 to the -8. You do expect, right? And you take like the transition like a 0.5, you know, like the spherical accretion. Then you get like m dots transition truncation radius between 3 and 5. Now, for more evolved objects, it's the other way around from what you said, because magnetic fields don't necessarily are going to decay, right? In fact, the stars are going to rotate faster because they're not coupled to the disk in cases, right? And then in addition, because the m dot decreases with time, you see the fact is that you expect that it goes outside co-rotation. If it goes outside co-rotation, it cannot accrete anymore. So it's the other way around, actually. Now, if we talk about the Herwigs, that's different, right? Because there is a transition at some point, which Halcyon probably will talk more about that, that then, no, it was mentioned yesterday, sorry, by Rene. The structure of the magnetic field, it changes from dipolar to some more complicated things, and then that's another story, and still to be understood. But for T-Tauri stars, I think that's fine.
Okay, so I think we're pretty much out of time, but we'll take one quick online question.
Yeah. Lynn, do you want to unmute yourself?
Sure, thanks. Nice to see everyone going by on the video. I'm wondering, as history proceeded to the present, the data got a lot better, as did the sophistication of the models. And so I'm just wondering if you can comment on that interplay. If we had, you know, way back when, if we had the fantastic Spitzer IRS spectra or all of the, you know, variable line profiles, high resolution, high time resolution photometry that we have today, you know, as opposed to 4 IRAS points where, you know, you just ignore the 2 longest ones because they're big beams, right? Can you just comment on the interplay of the sophistication in the models? And if we had all this data back then, would we have gotten the simple stuff right?
I can't imagine what Steve Strong would have done with the data that we have right now. You know, I can, it goes beyond, because these people were working with so little and they did so much, right? And we have so much now and do so little, actually, in comparison, right? So yeah, I don't know exactly what you want me to answer, but it is true, right? That if these people, like those pioneers, had all this data at that time, imagine what they could have done. Yeah.
I'm glad we didn't know about that stuff.
Okay, on that note, I think we can move on. I'm sorry to cut off this discussion, but we have to move on. So next we have Carlo Manara from ISO and Garking. Oh, sorry, Maria. And Carlo will talk about accretion processes in protoplanetary disk evolution. Thank you, Carlo.
Yeah, so I want to start really thanking the organizer for giving me this opportunity, which is really unique for me. Talking in honor of Lee is a great honor for me. I want to start with acknowledging also for PhD students that are highlighted on this slide. Rick Leis just started at ESO, and Jessica Erkal and is actually there in the room. You can meet her. She has a nice poster about helium lines, so some of Lee profiles and also Susie's profiles, I would say. Giulio has just started here, and Gabriella is also showing a nice poster. I'm also mentioned later in the paper, in the presentation. Of course, all the students all got this book shown to them. You can see a nicer version of the one of them Megat, but that's not because I read it less. It's simply because I got it from my mom, and you know, Italian moms like to do things properly for kids, so I got it covered. So you can keep it for more years, and you can travel with it and actually read it all the time you want. When I was preparing this talk, I really thought about the sentence that recently the new Nobel Prize Parisi said when he got the prize. He said, "We're standing on the shoulders of giants," and this is, yeah, someone already said it before, but for me, this is clearly how I can describe the relationship with Lee. All what I'm going to explain or I'm going to tell you about starts from pioneering work that he did, Nuria did, Antonella, and many other colleagues did. And this is really, for me, a great example of how we can continue on this nice venue that he showed to us. So I start by showing this paper that was already mentioned by Nuria, and that a few of you probably have seen. Don't know if you have not seen it, please leave the room now. But right now, I would like to start with the situation that I think we are in right now, which is we're trying to really understand this aspect that Nuria mentioned about how the angular momentum is transported in the disk and what drives the accretion to the central star. And we're facing more or less a phase where we are looking at two main models. So this viscous evolution alpha disk model that also Lee mentioned in his 1998 paper, and another model where the accretion is not driven by viscosity, but it's usually driven by winds. But I also want to mention that there is a nice paper by Lee and Bai where they actually mentioned the possibility of having simple low viscosity in the disk and still drive accretion. The reason why it is relevant to understand the difference between these two models lies for me in the fact that they do predict very different disk surface densities, which in the end impact the way the planets are formed and the protoplanetary disks evolve in general. And my research recently has been really focused on trying to understand whether we can constrain which one of these models is the main driver of the evolution of disks and therefore of accretion. But in general, one should start from trying to test one simple model. And I want to go back, and I'll do it multiple times during the talk. I go back to the Arman 1998 paper, where he actually said, given the limited nature of the observational data available, we wish to apply simple models with a minimum of parameters. And this is where he starts to then tell us how to use the Lindenberg Pringle model. And I actually think that the first thing we have to do is to really test the limits of this viscous evolution model, as I will show in this presentation. In order to do that, one has to know how to measure the mass accretion rates onto the central star. And in the last years, here, I would say here in Europe, we actually have done quite some work using, in particular, spectra from the X-Shooter spectrograph on the Very Large Telescope, where we can actually get the Balmer continuum measurements, even if the nights are not extremely perfectly photometrical as the ones that Lee had in his lucky night. But we have actually started to apply this method to multiple stars and to survey different star forming regions with the goal of determining this mass accretion rate in as many stars as we could. And one of the quests we had was to actually verify the relation between disk mass and mass accretion rate. I go back to the paper of Lee, where he actually already simply describes that in the viscous evolution scenario, one would expect a correlation between the global disk mass and the mass accretion rate of the central star. And he also tries to find this relation, which of course could not be found given the limited number of data points that were available. But but this is clearly, in my opinion, right now the best way to actually test these models, to measure disk masses and mass accretion rates for stars. And what we now think the picture looks like is more or less what you can see in this schema from Giovanni Rosotti, where we actually expect a tight correlation between the disk mass and the mass accretion rate in a purely viscously evolving disk, with a ratio between these two quantities that should be more or less the age of the targets. And then we expect other processes to actually create either a spread or move targets around in this plot. This is the starting hypothesis we had. And this is how we actually try to combine the measurements of mass accretion rates from Mendiak shooter and disk masses from ALMA. And a few years ago, we were actually able to show that taking the data in the lupus star forming region, there is a correlation between these two quantities. But there were already a number of surprises. I mean, it was a nice result, I think, but there were a lot of surprises. First of all, the correlation was with the dust mass, which is weird. So we had to assume a constant gas to dust ratio to actually assume that the correlation is with the global disk mass. And secondly, the slope was not exactly 1, as we would have expected. And third, there was a spread of values around the best fit. So we started to play with viscous evolution models. And of course, Lee liked to play with it in the past. Now we have Giuseppe Lodato in Milano, who actually still likes to play with it a lot. And he managed to find a fit to the data that could actually reproduce the observations we had with viscous evolution models. But there was a big assumption here. In order to reproduce observations, we had to assume that the viscous timescale that is regulating the evolution of disks is quite long, is about 1 megayear. And we, of course, understood that if that was the case, to actually find this correlation that becomes tighter at times much longer than the viscous timescale, one has to go to older star forming regions to test if this spread becomes smaller. But this is, of course, like most of what I do, this is already written, at least the idea, in previous papers. So if I go back to Lee's paper, one can actually see that he was already at the end of the abstract suggesting that we have to go and look at older samples of stars to study disk evolution. So a few years later, I actually managed to do this and to go to the upper Scorpius star forming region. We already heard something about this in the previous talks. But once you go in the upper Scorpius star forming region and you measure the mass accretion rate and the disk masses, shown here in yellow, you actually find another weird result. You actually see that the values of the mass accretion rates at any given disk mass are actually too high with respect to what we would have expected with viscous evolution model. In particular, what we see is that there is a large spread of values at any given disk mass, whereas we actually expected a tighter correlation according to viscous evolution models. And the other thing is, indeed, we see little evolution of the mass accretion rate with time, at least for these low disk mass objects. This is definitely something intriguing that we still have to understand. There is the possibility that what we are tracing here is actually the effect of the evolution of dust rather than evolution of mass accretion rate. And this is, for example, what is discussed in recent papers by Andrew Selleck. But there is also the possibility that the way to explain the evolution of disks is actually not the viscous evolution model. I will not mention too much, but I want just to point to the fact that there is now a new work coming out soon by Benoit Tabone, who actually tries to have, who's actually succeeded in describing the disk-wind evolution model in a similar way as the simple viscous evolution model with a sort of alpha-like parameter. And it can definitely reproduce the observations we have of the disk mass versus mass accretion rate relation and explain most of what we know as an effect of a disk that is evolving through disk winds. So as you will see in this paper, it is now really possible to actually test not only the viscous evolution model, but also the disk wind model with a relatively low number of parameters. So from this point of view, it's, in my opinion, still, the question is still open of what is the driver of disk evolution, but we are now at a stage where we have the observations to actually test the models. And we have the real predictions from all the models that can describe disk evolution. I just want to also mention a couple of other useful additional results that we obtained in the past, in the last years, actually recently. One is related to the fact that if you look at this plot, you actually see that we write that we expect external photoevaporation to drive the mass accretion rate to higher values at the given disk mass. And this is something we recently tested with Giulio Bettoni in the Sigma Orionis star-forming region. You see here on this plot that we added these cyan data. These are actually measurements of accretion rates and disk masses in Sigma Ori. And we combine this with the observations of forbidden lines that also other groups have been doing. And we actually tried, and we're actually probably finding some effects due to the presence of strong external photoevaporation from the central star, which is, in my opinion, extremely interesting. And I also want to touch on shortly touch base on another point that also Nuria brought up, that Lee has always studied how the mass accretion rate evolves with age. I personally find complicated to trust the isochronal ages. So I think that one of the best ways to actually study this process is to actually go to the earlier phases. As Nuria showed before, if one goes to the class 1 phase, one can try and trace this evolution of disks, of mass accretion rate. I just wanted to point to recent work that we did with Eleonora Fiorellino, who is now a postdoc in Concoli. And she actually measured the mass accretion rate in one region where we actually have both class 1s and class 2s observed in the same ways. And we actually measure the mass accretion rate from the infrared lines like the bracket gamma and the Paschen beta. And we actually find that indeed the mass accretion rates in these earlier phases of evolution are typically higher than the one in class 2s. This is, in my opinion, a good way to actually start to study class 1s and earlier phases. So to move really to the infrared where the effect of extinction is anyway a little bit smaller. And I would 2 minutes. So if I have 2 minutes, I will just mention that that we are also working on accretion variability, but there is a poster by Gabriela, you can look at that. I want to use the last 2 minutes to say what, in my opinion, is the perspective of how we can study accretion in the future years. One of the big things we had in the last years is that there were these nice HST spectra that Nuria, Lee, and many other people were using. And there were also these ground-based spectra, for example, the X-shooter spectra. But right now, I think we are at the start of a new stage where actually these kind of data are available to everyone. This is thanks in particular to the Ulysses initiative from the director of HST, who is actually studying a lot of young stars, about 100 young stars with HST. And thanks to the work of Greg, Catherine, and many others, we're actually putting together the whole community to actually study these spectra together with other spectra that we are obtaining from ground-based observatories. So we will now have a complete view of the spectral energy distribution of disks of actually accreting stars from the UV to the optical. And this is just to show you a little bit what kind of data we're going to get. We're going to get HST data. We're going to get X-shooter flux calibrated spectra from 3.3 to 2.5 micron and extremely high resolution spectra. So if Nuria was already happy to see 30,000 resolution, we're now getting to 140,000 and we're studying accretion at these levels. This is, for example, what Gabriela Gidi shows in her poster. Just to show you what kind of data we're going to get. So this is a plot showing the data we have in the various star-forming regions. So we cover a pretty large range of stellar masses and ages, which is particularly interesting. And we already got quite a lot of data. So last year we got the Orion data, and now recently we got data in Lupus and in other star-forming regions. What we can do is, of course, measure the mass accretion rates, for example, from ground-based spectra in this region. This is shown in this paper, of which I'm particularly proud because it's the first time I have a paper with Lee, although he's one of the authors. And we can do something that is, in my opinion, extremely interesting, which is to finally compare what we measure as mass accretion rates from the Balmer continuum with the real excess in the UV. So we will test these volumetric correction, basically, we are using. The first tests are very promising. We are underestimating the excess flux, but by a factor of a few. And further tests that will be carried out by this collaboration. This is, of course, some of the results we're going to get. I just show here two recent results from our ground-based observations, where we actually found a new spectroscopic binary in OB1, and we actually found a rotation and rotating and unfolding material in one of these Orion stars. But with this, I conclude with just 2 points. The first one is really a thank to Lee, because I have learned in the years when he was coming, for example, to Munich to visit Andy Burkert, and I was bothering him getting in his office, and as soon as Andy was leaving, to actually ask him things about my data. I really learned how to really use the data to learn about the physics that's behind disk evolution. And I really think that we are now at the stage where we are combining the efforts to actually better constrain accretion and ejection mechanism. So it's a very promising time to continue on his legacy. Thank you.
Thank you very much, Carlo. Have we any questions?
Thanks, Carlo. This is Patrick speaking. Thanks for the nice talk. So you mentioned the class 1 object where you see even larger accretions. As you know, or we all know, class 1, of course, they are still accreting from the remaining envelopes. And the classical paradigm so far has been that matter will fall onto the disks, essentially because of conservation of angular momentum, and then be dragged through the disk. But as you mentioned, magnetic braking through magnetic field, obviously, is more and more considered. And actually, in recent simulation, we found that because of magnetic braking and magnetic field, there is actually the possibility that some of this material is actually not falling into the disks, it's falling directly into the star because it's losing angular momentum along its way through magnetic braking, exactly like in the wind model, except that it does not need even go to the plan and come and then lift. It just goes straight to the star. And so I was wondering whether in the context of your class 1, where you should have accretions, that's something which rang a bell. And at the very end of your talk, you mentioned this piling gas, which is accreting. And I was wondering again, whether that's maybe something related to what I just described.
Sorry, can you repeat the last part? I mentioned
sorry, at the very end of your talk, you mentioned in these new observations, the possible evidence for spiraling and accreting gas. And so I was wondering whether this could be somehow related to something which matters, that is, as it is accreting toward disk/stars, on its way is losing angular momentum because of magnetic braking essentially, and therefore it may never reach the disk and fall directly into the star.
Okay, thanks. Yeah, so about the first part of the question, so the accretion rates we measure in these class 1 objects are those on the star, in the sense that at this stage in the near infrared we already see the photosphere. So these are phases where we can already see the photosphere of the star, and the bracket gamma and Paschen beta line are measured, accreted, emitted close to the central star. This is of course the assumption we do. So we use, for example, the relations that are valid for class 2s. This is something that we have to verify. So in a certain way, I'm not sure we're going to trace exactly what you were asking. And the recent observations that I mentioned could actually be what you say, but this is a class 2 object. This is a much more evolved and older object. And this is actually observations that we do in the optical. So from a spectroscopic point of view, I doubt we're going to have the same kind of observations for class 1s for some time, because this is very high resolution in the optical, whereas there it's low resolution in infrared.
Okay, so Lee has.
Yeah, so Patrick, in terms of your question, we've known for quite some time with based on spectral energy distribution modeling of the overall SED is that if you had complete radial infall or mostly radial infall, you'd have too much extinction, and then the shapes of the spectral energy distributions wouldn't fit. I mean, for class 0s, you might have something like what you're talking about, but for the class 1s, you really need to have, you can't have it go all the way directly into the star just because of the dust extinction. And also we've got outflows, right? So you know, the outflows prevent stuff from landing right on the star. So Carlo, that was a great talk, despite the fact you didn't use my cartoon.
I actually had to remove it after Nuria commented on it. No.
I want to make, I'm sorry to indulge my, well,
No,
the hell with it.
yeah.
I do have a question, but I just wanted to say about the viscous evolution similarity solution. Sometimes you do stuff that if you had thought about it more, you wouldn't have done. You know what I'm saying? You just go for it, right? And then you find, oh, well, why did I do that, right? But sometimes those can be like benchmarks. You know, this is a toy model. It does this. It has the minimum parameters, and then you find out how it doesn't work, or whatever, right? And I think a lot of times just finding out what doesn't work is what we can mostly do. I just wanted to ask for your class 1s. Did you compare those accretion rates with anybody's estimate of an infall rate from the set?
In that specific case, I would have to check. I don't think we did it. Yeah, I'll have to check.
Okay, so would we have any on then? No, yeah, I think we need to move on. Okay, thank you very much, Carlo. Okay, so next we have Shinsuke Takasawa from Osaka University talking about 3D MHD modeling of magnetospheric accretion. Okay, we're ready.
Yes, thank you. Thank you for having me in this great conference. I want to introduce our recent numerical study on magnetospheric accretion. We often find jets and winds in classical T-star systems. Jets are often surrounded by slower conical winds. We generally consider that those outflows are driven by strongly magnetized stars and inner disks. My study is greatly inspired and motivated by many pieces of work by Professor Hartmann, and I want to understand the detailed connection between the accretion and outflow structures. Recently, very careful spectroscopic observations have revealed the properties of jets and winds. For example, Banzati et al. Found a set of classical T-tauri stars that show jets and conical winds. The conical winds have a velocity smaller than 50 km per second. The conical winds with broader line spectra are considered to emanate from very close to the star. If we compare this structure with a classical model, for example, the polar stellar winds may be a part of the jet, and the disk wind would correspond to conical jets. And Professor Romanova and her colleague performed many simulations of magnetospheric accretion and studied the conical wind structure. They found that a strong disk wind from the outer edge of the magnetosphere, and the wind is driven by magnetic pressure gradient. The point is that the velocity is about 100 km per second in the simulation. So the conical wind structure is commonly seen in previous 2D simulations. However, the speed in 2D models seems to be very large compared to observations. So 2D models must be missing something. And there is another mismatch between the theoretical models and observations. 2D models commonly show magnetospheric ejections resulting from the star-disk interaction. And in simulations, the ejections generally cause significant time variability, including huge flares. However, observations do not fully support this idea. For example, the X-ray observations suggest that high accretors produce less powerful flares. This plot shows the cumulative distribution of flare energy for stars with different accretion rate. This plot shows that the stars with high accretion rate produces less powerful flares. So the observations and theoretical models are not fully consistent. So what are we missing? So as our current understanding mainly relies on 2D models, maybe 3D physics will be a key to resolve the problems. So many studies assume that the process of around here, for example, the process of the gas invasion into a magnetosphere is a diffusive process, and the effective viscosity and the diffusivity arising from the turbulent diffusion are applicable. But these assumptions should be examined using 3D models. We have been performing 3D simulations of accretion onto the star from a turbulent accretion disk. This image shows an example of our model without the magnetosphere. In this talk, I will introduce our recent 3D simulations of magnetospheric accretion. And we will discuss 3D effects. Here is a setup of our 3D models. We assume a spinning star with a magnetosphere and a magnetized torus. After the simulation starts, the torus becomes a turbulent accretion disk. We also assume the coronal heating just around the star. As a consequence, the star blows a thermally driven stellar wind from a tenuous stellar corona. Please note that we have a very tiny time step in our simulations, which makes numerical simulations very, very difficult. After many trials and errors, we succeeded in performing simulations and getting meaningful results. Today, I will show the results of two models. The one is for fast rotator, and the other is for a slow rotator. This movie shows the general structure of a fast rotator case. Here is here the density is shown, and we can see the magnetosphere here, and the temperature map shows a hot stellar wind, cool disk, and hot ejections. And the radial velocity map indicates that the accretion around here. So the magnetic accretion occurs mainly in the southern hemisphere in this case. So what is happening here is that the accreting gas pushes the magnetosphere to the one side, and the gas falls onto the star on the other side. This structure is stable in terms of the angular momentum transfer. And this movie shows that magnetic ejection do occur, but the flaring activity is not very prominent as expected from 2D models. In fact, the plot of this accretion rate shows that weak time variability. I compare our model with the previous 3D model. This is a pioneering model by Romanova et al. And this is our result. As our simulation has a better resolution, our model captures finer scale structures. So from now on, I want to focus on the following two questions. First, why are magnetic ejections not as violent as expected from 2D models? Let's think about this first. There are some reasons for this, but here, because of the time is limited, I focus on the energy buildup process in this talk. We found that the energy buildup in 3 dimensions is more difficult, more inefficient than in 2 dimensions. This movie shows that the midplane density and plasma data. Here we can see accreting gas invading magnetosphere. But please note that the accreting gas quickly falls onto the star before twisting up magnetic fields. So this result is a direct consequence that the invasion process is not the diffusive process. And therefore, the patchy accretion flows can twist only the outer part of the magnetosphere, where the magnetic field strength is weak. These results lead to an inefficient energy buildup, and makes flares to occur, makes powerful flares to occur. And next, I want to discuss the conical wind. Can magnetic accretion produce a slower conical wind? So we investigated the latitudinal structure of outflow. This movie shows that the density of a slow rotator case. We measure the physical quantity around this half circle. And this plot displays the velocity. The black line shows the velocity, and this line shows the temperature and density. And we can find 3 structures here. The first one is the cool and slow disk wind. The speed is about 10 km per second, and the temperature is about 10 to the 4 Kelvin. The second structure is a pressure-driven stellar wind around the pole, and the third one is interface layer. So our 3D model produced a slow conical wind here. This picture shows a three-dimensional structure without and with the disk field lines. The gray lines show the disk field lines. The conical wind emanates from from around the outer boundary of magnetosphere. And 3D fields in the disk here are mainly toroidal, and the conical wind is driven by the magnetic pressure gradient force of the twisted field lines, as found in previous studies. A caveat here is that the centrifugal force is minor in this case, although the inclination angle is greater than 30 degrees. The wind is magnetically accelerated, but the plasma beta in the wind region is moderate. So this movie shows the plasma beta around the star, and you can see that in the wind region around here, the plasma beta is about 1 to 10. Therefore, from the energetic point of view, the wind speed cannot be as large as the Keplerian velocity of the wind base. To highlight the wind acceleration, we check the wind property along the streamline shown in this figure. This line, the black. So in the right panel, the black line indicates the poroidal velocity. The wind gas quickly passes through the slow and alpine points and gradually approach to the fast point. And an important point here is that the wind speed is close to the sound speed, the blue dashed lines. This is because the wind experiences the gradual magnetic acceleration with moderate plasma beta. So now I want to discuss 3D effects on wind speed. First, let's consider what happens in 2D in 2 dimensions. At the inner disk, the toroidal field is generated from the stellar magnetosphere via disk shear. As a result, a strongly magnetized region forms above the disk. The magnetic pressure gradient force in this region drives the conical rotating wind like this. And this diagram summarizes the energetic discussion. At the beginning of field amplification, the magnetic energy density is the smallest among the others. But as a result of disk shear, magnetic energy density increases up to the gravitational energy density. Therefore, the wind speed can be comparable to the Keplerian velocity of the base, as seen in the 2D models. But the story becomes different in 3 dimensions. We have MRI turbulence, which tries to diffuse out coherent magnetic field. In addition, we have a magnetic buoyancy instability or Parker instability. The Parker instability prevents the amplification of magnetic fields by removing the toroidal fields from the disk. When plasma beta is unity, the growth timescale of Parker instability is comparable to the orbital timescale, and the instability efficiently removes the magnetic fields from the disk. As these 3D effects prevent the field amplification, the wind velocity becomes much smaller than the Keplerian velocity of the wind base. Okay, so this is a summary slide. So we have investigated the 3D effects on magnetospheric accretion with particular focus on magnetospheric ejections and conical winds. And in this model, we studied how the gas invades and twist up magnetosphere. And what we found is that the star-disk interaction is not a simple diffusive process. So we need to include the 3D effects. And in this model, that we studied how the conical wind is driven and what determines the wind speed. And we found that the 3D effects like turbulence and Parker instability limit the magnetic energy density in and around the accretion disk. Okay, thank you.
Thank you very much, Saku. We haven't talked yet.
Thank you for the interesting talk. If the energy is less than when you do 3D models in the outflow, where does the energy go?
So are you talking about this?
Yes. Yeah. So you do the 3D. There's less energy going into the flow outwards. But where's the energy?
Energy is continuously ejected from the disk. But the point is that the energy density, the relative magnitude between the magnetic energy and the gravitational energy. So the total energy, I mean for example, the generation rate of the magnetic field, magnetic energy would be similar, but of course it depends on the field strength in the disk. But the point is that the relative magnitude between the energy density.
Okay, Lee.
Okay, thank you.
Yeah, in 2D models, in 2D models, magnetic energy is extremely enhanced in the disk, and the plasma beta can be lower than unity inside the disk.
So I'm not really good at MHD, so I'm just trying to understand. Starting with Ian's question, is it there's diffusion of the magnetic energies is going away because of this turbulent diffusion of the field? Is there reconnection involved in that? Is that within the disk? Is that what's going on? Because I'm also thinking.
Right. Yeah, reconnection is important inside the disk. As MRI produces the channel flows inside the disk, the channel, maybe you don't see me there. So channel flow produces the current sheet inside the disk. But in 2D models, there is no way to reconnect the field lines because the anti-parallel field lines are in the azimuthal direction. So the magnetic field is continuously amplified. Toroidal field is continuously amplified. But in 3D, we can expect a reconnection between the azimuthal field lines. That's partly limit the increase of the field amplification.
Okay, and is that reconnection then? That's how the stuff that accretes into the magnetosphere, is that instead of a diffusive process, it's some kind of turbulent reconnection thing that allows the gas to get on the field lines and accrete in the magnetosphere?
Yeah, it's very difficult to answer. I'm still investigating how the disk gas is supplied to the magnetosphere. For example, even in the low accretion rate case, we do see the invasion of the gas into the magnetosphere. And the other thing is that we have an MRI-driven wind away from the star, and some of the gas is falling onto the star away from the starting point of the gas accretion is away from the star. So there are many passes. But yeah, of course, the main accretion rate, mainly the accretion rate should be determined down here.
Okay, so I think we have one last question from Patrick, quick, and then we can break for lunch.
Yeah, thank you. Very nice talk. I wonder, I'm always wondering about the boundary conditions of the magnetic field into the star, because probably you are doing some assumption, and I wonder whether at the end of the day, it would not be necessary to have a model which takes into account both the evolution of the magnetic field into the star and in the accretion in the surrounding medium. What do you think?
Yeah. Well, my boundary condition for the magnetic fields are fixed, and the magnetic fields are rotating with the stellar surface. And the time span, I think that the question is related to the time scale, what we are interested in. So in this simulation, that we follow the half-year evolution in this simulation, and the point is that the global scale magnetic field structure will change the significantly changes on the time scale or not. And here I assume that the global structure doesn't change much during that time span. That's an assumption. Thank you.
Good feeling is that it's something, is it an important next steps, or do you think it is fair?
Yeah, yes. Yeah, it's very important to update the model, because, for example, the formation timescale of sunspots is about on the months, on the timescale of months also.
Thank you.
Okay, so I think we really need to leave it there. So thank you, Shinsuke, and all of our speakers from this session. First, we have an invite. Yeah, that's okay. First, we have an invited talk from Sylvia Alencar, who's going to talk to us about time series spectroscopy and photometry and how it can be used to probe star disk interaction. So Sylvia, we're ready when you are.
So first of all, it's a pleasure to be here, and thank you all for the invitation. I mean, I've been following Lee Hartman's works forever. Since I began working on star formation, I've had the pleasure to work with Lee in a few papers, and always ask him lots of questions that were promptly answered. And so I'm very happy to be able to present this talk. I'm going to talk to you about the importance of the time domain in spectroscopy and photometry to understand what's going on in the inner disk regions. So let's do it. Well, we've been seeing these amazing images of circumstellar disks around young stars by ALMA and by SPHERE and other instruments in the last years. And I particularly like the transition disks, which are the ones that are shown here from a work by Francis Antoine de Marot. These are ALMA continuum emissions, so these are the large scales. It turns out that all these systems are accreting systems. So there's a lot going on in the inner disk region. And we knew that for a long time. I'll take as an example, Lick calcium 15, that has been, the spectral energy distribution has been studied in detail by Catherine Espaya over a few years. And she has shown that inside this gap, inside this 50 AU gap, you have a star, of course. And we also have an inner disk that contributes to the SAN. And we have optically thin dust there too. And then finally, the outer disk, which is what we are seeing there. So there's a lot going on inside the gaps of these disks. And it's very interesting to think about how can we connect the small and the large scales to get a complete picture of what is disk evolution and star formation as a whole. So I'll zoom to the small scale, and before changing the slide, I'll say, sorry, Carla. We got it again. Nuria has already explained this, the magnetospheric accretion model very well. I'll just remind you that in the accretion flow, in the accretion columns, you form broad and strong emission lines, which can have blue shifted absorptions due to absorption by wind, and red shifted absorptions due to absorption by photons emitted in the hotspot and viewed through the accretion column. And it turns out that the main actor of all this, everything that is going on at the small scales, I'm talking about 0.1 AU, is the magnetic field. So it controls activity, accretion, the star disk interaction, the inner disk structure, and outflows, stellar winds, disk winds, and jets, and also the angular momentum transport. Those are contracting stars. They are accreting high velocity materials, still they don't rotate fast. So, and some very interesting systems to study this in a disk region are the high inclination systems, because our field of view go through our line of sight, go through all these structures. We pass through the disk wind, through the accretion column, the hotspot down to the star. And so it gives us a lot of information about what's going on in the small scales. Over the years, the magnetospheric accretion model has moved from this 2D axisymmetric dipolar field to 3D inclined dipoles, and then to 3D inclined multipoles, thanks to MHD simulations. And MHD simulations also may include accretion and outflows, as was shown before to us by Shinsuke Takasawa. And this is a simulation by Hiroshi Kurosawa and Marina Romanova. You see the magnetic field, you see the density profile, the density structure, and the velocity field with the arrows. All these simulations may show different types of outflows like disk winds, magnetospheric injections, and stellar winds. And recently, Georges Pontalmos, who is a postdoc with Jean Bouvier in Grenoble, has been doing some 2D and 3D simulations of the star disk interaction that I'm going to show to illustrate. I hope it works. Let's see. So as you let the system evolve, you form accretion columns. You have a zoom here, and you also form all these ejections. What is interesting about these simulations is that you can get still frames of it, and from the density, the velocity, and the temperature structure, you can do the radiative transfer calculations and get observables, line profiles, and light curves that can be directly compared to the observations. How do you do that? This is a little film by Benjamin Tessor, another postdoc with Jérôme in Grenoble. He's doing the radiative transfer calculations on top of Georges Pontalmos' 2D and 3D simulations. So this is the H-alpha emitting region of only the magnetosphere, and I'm going to show it at different velocity beams. At each velocity beam, you have an emitting surface that you can integrate the flux and build a line profile. So let's see, we'll start with at minus 100 kilometers per second, there's no emission in H-alpha here. So it's going. So as you move to minus 100 and 0 velocity, you see all the emitting region from H-alpha, and you integrate that flux at each velocity beam, and you build a line profile that can be directly compared to the observations. This was done by Marina Romanova and Hiroshi like 10 years ago. And they calculated, for example, the helium online in the infrared. And this is a good example of a star that has both the red shifted absorption and the blue shifted absorption, like the one that Maria showed us before. So you have accretion and outflow in the same star. And you can directly compare models and observations. This was also done by Hiroshi and Marina to calculate light curves. So this is the top panels here, the top curves here show the light curve that is the result of the rotating star with a hotspot, either a major hotspot in a stable accretion regime or many different hotspots that come and go in an unstable accretion regime. And these light curves can also be compared directly to the observations. Of course, you can do what I've shown here by Benjamin Tessor, had different rotation phases, and you get emission line profiles for the different rotation phases, and you can compare what the MHD predictions with the variability of the line profiles from the observations. And so the first thing you have to give to the MHD simulations is magnetic field topology. So what is the magnetic field of a classical T-tauri star? So you pick up your favorite object. At the time, this was my favorite object, P2129 of Fucus. And you do spectropolarimetry, for example, with Espadon at CFHT. Now we can also use Spirou in the infrared or Hubspol. And you get the Stokes I, non-polarized, and the Stokes V, circularly polarized profiles. And it turns out that the variation of the Stokes V is related to the magnetic vector in our line of sight. So the variation of the magnetic vector in our line of sight. So we can, from the Stokes I and Stokes V profiles, you can invert this time series into surface brightness and large-scale magnetic fields, and you get the magnetic topology of the star. So we did it for V2129 of Fucus. So we had this octopole and dipole magnetic field at the stellar surface. At a few stellar radii from the star, where the star and the disk interact, the dipole dominates because it decays more slowly. So you use this dipole and octopole magnetic field as an input to the MHD simulations. And you wait until it reaches a steady state. And what we got was this nice two magnetic field magnetospheric accretion columns, one in each hemisphere. And then Hiushi did the radiative transfer calculations. I show here the example of H beta. So for different rotational phases, you have the emitting regions, the emitting surfaces of H beta. You sum up the fluxes at the different velocities, and you get line profiles that you can directly compare. So this is not a fit. This is a direct comparison below. It's a direct comparison of the observed profiles and the model profiles based on the magnetic field structure that was measured. So that was really, really nice result. I should thank Greg Herzeg for it in a sense, because he put us all in a conference in Hindenburg Castle. During the winter, we were trapped there for a week, and I managed to convince Marina and Hiushi to do the calculations for me. So that was a very nice result, because it showed that the basic assumptions of the magnetospheric accretion were all there, and they worked together. There's a talk later by Alana Souza, who's going to show to you that this system was well behaved when I studied it, but it's not always the case now. So another very nice result is quite recent by Tanati Bodhi. This is a CVSO 1335. It's an evolved, in a sense, classical T-Tauri star. It's a 5 million-year-old solar mass star, very low mass accretion rate with a complex infall geometry. So sometimes just one accretion column in each hemisphere is not enough to explain what we observe. So what he proposed is that you have two accretion columns, and they both contribute to the emission line profiles. And this is also reminiscent of some old MHD simulations by Kulkarni and Romanova that showed that you could have this major accretion funnel and accretion tongues that come and go inside it. So things may not be very simple all the time. But to really study these systems, you see how dynamic they are. They change all the time. And so to really study these systems, you have to do properly synoptic, photometric, and spectroscopic surveys, because it allows us to probe several timescales like hours, months, days, and months, and to analyze the inner disk structure, the star-disk interaction, and the accretion process dynamics. And this was revolutionized by high precision continuous photometry from satellites, were actually launched to find exoplanets, which I love because they allow us to do other types of science. And it was just beautiful to see the light curves that came out of it. So Coho, Kepler, the K2 mission, and TESS have all observed star forming regions. Before we look at the light curves, let's just remember that accretion can occur in stable regimes and unstable regimes. In the stable regime, what is predicted is that you have these two major accretion columns, one in each hemisphere, like was the case of V2129 of Fucus. But you can also have an unstable instabilities in the inner disk, Rayleigh-Taylor instabilities that are favored by small misalignments between the rotation and the magnetic field axis. And if the magnetospheric radius is much less than the co-rotation radius. And this happens, for example, when the mass accretion rate is very strong. And in that case, you get these accretion tongues that come and go, that randomly come and go. The light curves that we observe also depend on the viewing angle, on the viewing angle. So suppose you have a star which is highly convective, has a strong magnetic field, and the magnetic axis is inclined with respect to the rotation axis. Then accretion is favored at certain phases. You form these accretion columns. If there is dust at the magnetospheric radius, and the temperature for a typical classical T-Tauri star, the temperature allows dust to be there. It's below the sublimation dust temperature. So if there is dust, the dust may be entrained by the gas at the base of the accretion column, creating an inner disk warp. And if you look at this system from medium to high inclination, you see this warp passing in front of the star as the system rotates. Of course, if you look at low inclination, you won't see it, okay? So it depends on the viewing angle too. So the first time I look at, these are Coho light curves from NGC 2264. All of these stars are classical T-star stars, they're all accreting. And the first time I look at these light curves back in 2008, long time ago, I was just amazed because they were so beautiful. They were like drawn by hand, except all the points were real. And so it had to tell us a lot about the physical processes at work. Coho went back to the NGC 2264 in 2011. There's a great paper by Marie Cody where she shows how to classify these light curves. But I'll go slowly in kind of each major type and telling you how we interpreted what was going on. So there were accretion burst light curves, so light curves where you have a well-defined minima and then it just bursts up, goes up all the time. This is the typical accretion burst light curve. In 2011, we also had Spitzer data simultaneous with Coho, and the blue here is Spitzer. And so they were all aperiodic light curves, the accretion burst ones. They really showed that accretion is non-steady. So we were just like looking at accretion occurring and in a non-steady way. And they were among the strongest accretors. We had simultaneous spectroscopy, high resolution spectroscopy. Here's the H-alpha equivalent with that, and in red are the equivalent with of the accretion burst light curves. And they're really, really strong compared to the spot ones and the deeper ones. All these accretion burst light curves, so they belong to the strongest accretors, and they have symmetric or P Cygni profiles in H-alpha. So they also had strong outflows. So have strong outflows, strong accretion, and that explains this type of light curve. So we could really pinpoint a major physical process that was dominating the accretion burst light curves, and these were 12% of our sample. Then you had stochastic light curves, which is a mild version of the ones before. They're also aperiodic, and light curve was due to variable accretion, but they had small accretion rates, and the light curves are really reminiscent of what is predicted by the unstable accretion model by NHD simulations by Marina and Hiyoshi. If you compare, it's basically the same. So you have the stones of accretion that come and go, and the hotspots that come and go too. The H-alpha profile, curiously, they all have this blue shifted absorption, but doesn't go below the continuum. So it's not a P Cygni profile, it's rather due to a disk wind. So those are moderate versions of the high mass accretion rate ones. And then there's the deeper light curves. Those are my favorites. So about 15% of the light curves were deepers, were periodic deepers, and 10% aperiodic deepers. So that makes a bunch of them. So that's 25% of the light curves were deepers, which really means that all of them have this type of inner disk warp, because to see a deeper, you have to see at high inclination, at moderate to high inclination. So if 20% of them had deepers, whatever we were looking at here was present in all the stars, in all the classical T-type stars. So the deeper light curve has a well-defined maximum that is interrupted by minima that vary in width and depth from cycle to cycle. So every cycle is a little bit different, but the minima occur at the same phases. So if you put it in phase, you see how different it can be at each rotation cycle. We were able to model it with a very simple model of an azimuthally distributed inner disk warp that changes in height. The scale height changes at every rotation. These were all high inclination systems, and they were moderate accretors. And the H-alpha profile this time showed both blue shifted and red shifted absorption. So that's exactly because we're looking at them through all these structures, because they're high inclination systems. And one thing that was really nice to go back to the same region 3 years later was that we could see, we realized that half of the deepers changed from periodic to aperiodic and vice versa in a time scale of 3 years. So it means that although we may be seeing a star in a phase of periodic variability and stable accretion, in a short period of time, it can move to an unstable accretion state. And I mean, 3 years was just the different time of observations that we have, but we don't know really the time scale. It can move from one type of variability to the other in even a smaller time scale. Then there are the spotted light curves, which are these well-behaved people. Sometimes people behave and stars also behave well. So they are very periodic, very symmetric. They are due to hot and cold spots. They're very stable light curves. They belong to moderate accretors, and one possibility is that these are the same stars as the deeper stars, but we're just looking at them from a different geometry. But they probably have the same kind of behavior in the inner disk. We're just not looking through the inner disk to see the occultations from the disk warp. So the ones I showed you were all light curves and data from NGC 2264, which was the only star-forming region that Coho observed. But then came Kepler in the K2 mission, and now we have TESS. And these are light curves from K2 in the light curves, the classical T-tauri stars from K2 in the Ho-off and Upper Scorpius regions. And you can see the same type of variability. This is a work by Mahikodi. And you can see the same type of variability. You have periodic light curves, quasi-periodic bursters, all due to accretion. Then you have the deepers. And I'm going to concentrate on those. And then there's a talk by Pauline McGuinness later on deepers in upper scope. And so now I'm going to focus on the deepers because they tell us so much about what's going on. So the deeper prototype back then, many years, was A Tau. It was the only star that we had been observing had done continuous campaigns in a sense, and they were organized by Jérôme Bouvier. It was always very complicated because you had to have telescopes all over the world to try to have data for like a month. The rotation period is 8 days. You wanted to follow it for like 2 or 3 rotation periods at least. So it was a tour de force to organize all these campaigns, and we wanted a simultaneous spectroscopy, so we were like all over for a month, observing from everywhere that we could find people to help us, and it was actually very interesting. And the ATAU was a great prototype. It worked perfectly well when we observed it. Now it's a bit crazy. All those stars, they come and go in their craziness. So A Tau showed that these periodical eclipses, it's a typical deeper, have a maximum well-defined and minima that vary in width and depth from cycle to cycle. And the period of the photometry gives you the period of the warp. So it's where the warp is located. So for this star, it was at 8.22 days. So it's the period of the inner disk warp. At the same time, we had a spectroscopy, and you see that during the minima, there's a huge redshifted absorption. This is H beta. There's a huge redshifted absorption that comes, which is exactly when the accretion funnel, the major accretion funnel passes in front of us, and you have photons from the hotspot, which are absorbed by the accretion column at high redshifted velocities. So, and this occurred with the same periodicity as the warp periodicity. And then you have the veiling, and the veiling increases exactly during the minima, showing that we are looking at the hotspot. So you have the base of the accretion column traced by the warp, probed by the warp. Then you have the accretion column itself by the Balmer lines, and then you have the accretion shock traced by the veiling, and they all rotate together. So that is a very good example of how the basic assumptions of the magnetospheric accretion model actually work. Later on, we looked at another star. This is Lick Calcium 15, the one I showed you, the spectral energy distribution by Catherine Spagliat before. So this is a transition disk with a huge gap at 50 AU gap. And the outer disk has an inclination of 44 to 50 degrees. And we know there's a presence of an inner disk because it casts shadows in the imaging obtained with sphere, and also due to the SED modeling. So this is an inclined, a system that is not very highly inclined. The outer disk is not very highly inclined. But then came K2, and if you look at the light curve of Lick Calcium 15, it's a true deeper. And it's a periodic dipper. And it's there, there's no doubt about it. If you phase it, you phase it with a period of the region where the warp is located. So the rotation, the period of the warp is 5.7 days. So we know it's located there. But then how can a transition disk be a dipper? You have to have an inner disk. You really need an inner disk for the inner disk to occur the star periodically. But dippers have inclinations of 55 to 75 degrees, according to Pauline, who's there in the room. And so while the calcium-15 outer disk has a much lower inclination. So the only possibility was not only that we had an inner disk, but it was tilted with respect to the outer disk. And it turns out that we could, for example, calculate the inclination of the star with respect to a line of sight using V sin I, the stellar rotation period, which happened to be exactly the same as the warp, as the period that we got from the warp variability, and the stellar radius, and you get that the inclination has to be, the stellar inclination with respect to a line of sight has to be larger than 64 degrees. So that's okay. So what we have is an outer disk, and inside it you have a dusty inner disk inclined with respect to the outer disk. And then, okay, you can have a dipper there. So we had spectropolarimetry. We could reconstruct the magnetic field, which is actually axisymmetric. It's a colloidal magnetic field dominated by a dipole, a strong dipole of 1.35 kilogauss. So we had all kinds of variabilities, things that you can measure, and they were all quite periodic. We got the stellar rotation period from the radial velocity variations, and it turns out to be exactly the same as the one you got from the light curve due to the warp. So it means that the warp is located at co-rotation. Another important thing is that, for example, we got the variability of the longitudinal magnetic field, and it actually goes from 0 to like 700 Gauss very rapidly with the same period, meaning that the inclination has to be high, because at some point you don't see the magnetic field vector pointing at you. So you really can't be seeing the hotspot all the time. And this was also seen.
5 minutes, Sylvia.
This was also seen in the calcium-15 in the helium online. So it varies a lot, but it appears only at certain phases, and it disappears completely at other phases. It varies at the stellar rotation period, mapping the hotspot. And when it disappears, it means that the inclination has to be high too. We could also see that in H beta, in the redshifted absorptions that only appear at certain phases, so mapping the accretion column. So if you put it all together for calcium-15, what you have is that it's a pre-transition disk system with a periodic dipper. There's a colloidal stellar magnetic field with strong dipole. The magnetospheric cavity reaches out to the co-rotation radius. And observationally, there is a strong relation between the inner disk warp, the accretion column, and the hotspot mediated by the stellar magnetic field. It's a dynamical star-disk interaction with a misaligned inner disk inside the 50 AU gap. This is, I used the cartoon from another object that I studied by Aurora Cecilia Aguilar, but it's the same kind of idea. You have an inner disk which is inclined, and we start to link the small scales to the large scales. I'll just finish by talking rapidly about TW Hydra, which is highly accretive. It's an old star, but it has strong accretion. It has a dipole and an octupole field. And we know that it has a strong disk, an important disk, and the ALMA images are beautiful, showing that there's an inner disk gap at just 1 AU, but inside the gap, there is accretion going on. And this was a beautiful result recently that Rebecca Garcia Lopez is going to talk more about, I suppose, later on today, that VLTI gravity obtained. So they mapped the inner edge of the dusty disk at 0.04 AU, that's sub-AU scales from the K-band continuum excess. And inside it, they got the bracket line emitting region, which is very compact at 0.02 AU, marginally resolving it. So there's emission from bracket gamma coming from the magnetosphere, which is inside, which coincides with what is expected for the size of the magnetosphere, given the measured dipole field of 700 Gauss. So that's simply beautiful, and that really links the inner and outer scales. This is just a cartoon showing what's the inner region of TW Hydra. And remember that there's this 1 AU gap, and this is inside the 1 AU gap. We're talking about sub-AU structures. Then I'll wrap up with 4 conclusions, all in images. I'll just remind you that after all these years, the magnetospheric accretion model is still standing. That star disk MHD simulation definitely bridged the gap between theory and observations, allows us to really probe the dynamics of the inner disk regions. That multi-wavelength and multi-technique observations in the time domain are needed to understand the star disk interaction and the dynamics of the inner disk region. And finally, that we're starting to be able to link the small and large scales in classical T-type stars. Thank you.
Thank you very much, Sylvia. Very nice talk. Do we have any questions in the room? Lee?
Sylvia, I was thinking that presumably for the dippers, the magnetosphere has to lift up dust, right?
Yes.
And so that means that the magnetosphere has to have some effect at least 2, if not beyond, the dust destruction radius.
Yes.
And potentially that radius could be bigger than co-rotation.
Yeah, in terms of temperature, yeah.
So my question is, and of course we want something at not much further than co-rotation or even inside of co-rotation to accrete, right?
Yes.
So I wondered, does this tell us anything about the range of radii over which the magnetic field penetrates the disk?
Well, yeah, for a typical classical T-type star, you still have, it can have dust at co-rotation in the sense that you have a temperature which is compatible with being smaller than the typical dust sublimation temperature, like 1500 K. But it's true that depending on, like for TW Hydra, for example, the dust, the inner dust disk is beyond co-rotation, which is it is true. We do see a lot of dippers, and when we look at this 1, 2, 3 million year old star forming regions, so either there's still dust near co-rotation, or the magnetic field reaches further out. There's no reason why it wouldn't reach further out in a sense, but it might be. It's more difficult to accrete. It's not impossible. From the MHD simulations, actually, they show that even in the propeller regime, where you are beyond co-rotation, you still have accretion. You still have accretion going on. So it's I don't know. Maybe there are some magnetic field lines that interact beyond co-rotation, but some that interact inside co-rotation, and gas can move to smaller radii and still accrete. But accretion doesn't really cease, even if you go to the propeller regime, where the magnetospheric radius is beyond a little bit of co-rotation.
Yeah, I was just asking because the range of penetration affects how you understand breaking.
Yes. Yeah.
Okay, we have Antonella online.
Yes. I have a question or a curiosity more about the dippers and the misinclined inner disk, because I haven't done any proper estimate of that, but it seems to me that we have many, and that if you look at the inclination of these dippers, many of them are quite face on according to the inclination of their outer disk. So there is a need for a misaligned inner disk in a significant fraction of disks of various kind of properties. Do you have any thinking about that? Yes,
well, there are only a few that are really face on, but they are. You're absolutely right.
And many that are really, things like this,
But they do exist. You're right. And even though, even if they are not face on, we still see a lot of, those shadows in the outer disks. And when you have information from the inner disk from accretion, for example, as we had for calcium 15, we really have the inclination of the star, which is different from the outer disk. And so and if I understood your question correctly, you want to know what misaligns those, right? What
do you think about that? You must have thought about that.
So I've seen a presentation recently by François Ménard, where he showed that you need not only a kind of one possibility is to need a planet outside the inner disk and inside the inner disk. You need actually two planets to keep this thing misaligned, not only to misalign it, but to keep it misaligned. So those are great candidates in a sense to look for perturbers. Something must be acting dynamically to misalign, and it's not only the inner disk which is misaligned; it's the star itself which is misaligned with.
No, yes. An alternative you have seen is that you can misalign the outer disk if it is accreted at the later stage. That's another possibility that we don't think much about.
Yes.
Probably doesn't work in many cases.
It's huge, isn't it? I mean, to misalign this outer disk, we're talking about, scale. I mean, it's a huge scale. I don't know.
It is a huge scale. Yes, it depends on where the star is. But what I find it interesting, all of that, because there are too many in a way. If it was just 2 or 3, sure. The system of 2 planets, I think it also requires a very specific range of the masses of the 2 planets. Otherwise, it won't be stable. So anyway,
but if it's another star, I mean, you could think of binaries, for example. If it's another star, we should see them with all these high resolution images that we're getting now. So that's the problem too. I mean, you have many binaries, right? And binaries are so common. So you could have binaries that misalign, one with a disk and one without, and then you misalign the other disk. But you should be seeing them, detecting them, and we don't. So that's the idea, to put in the planets to act dynamically on the inner disk. But yeah, it's an open question, I guess, because it's been there for not for many years that we're starting to see that.
They are still young and interesting.
Yeah. Okay, do we have any more questions? Okay, so we should thank Sylvia again. Okay, so next we have Adam Ginsberg from the University of Florida, who's going to talk about how massive stars get their gas.
All right, hi folks. So I'm going to take us in a bit of a different direction, talk about how high mass stars are getting their mass. And I've put in this line about binary stars. I'll tell you what that means in a minute. But I wanted to start off with a question that we also heard from a talk earlier from Tyler Borks. How does accretion end? Okay, we know that a star accretes gas from its surroundings, great, and its final mass is going to be set when this process stops. And I'm going to be arguing kind of that the process stops once you have a disk, a really clear disk with high mass stars. So I want to address the question in a few ways. What stops mass buildup? So there are a few options, right? You can just run out of the gas. So I'm talking kind of more on core scales here, bigger scales than we've been talking about in the last few, to reorient you guys. So you can run out of the gas. You can have a star be ejected from its mass reservoir. And this is something I think we haven't talked about much yet, but is an important process. You can blow out the gas, right? We've talked about feedback already. Evacuation would be the term for this. You can also have another star come along and steal it, sort of in the competitive accretion scenario. This is also sometimes termed fragmentation-induced starvation. So what's the role of disks? So we do know that high mass young stellar objects do have disks at various stages. There's evidence for this in different ways, but and you can debate what the definition of a disk is, but they have them. So there's a question of how and when does the mass get from the disk to the star? So I want to argue that this is going to happen. This happens mostly during what we might call the stage 0 phase. And I'll refer back to Tyler's talk, and he argued that this is the case for low mass stars. I'm saying it's actually kind of the same thing for high mass. And I'm going to argue, based on limited evidence, that this is largely happening through accretion bursts, or that at least that accretion bursts are a really important mode to move the gas onto stars, particularly in the high mass case. So these can be driven by a few different processes. Like one would be asymmetric and specifically non-axisymmetric accretion flows, dynamical interactions. And these are the two things I'll be talking about. I included also, yes, disk instabilities, possibly, and smooth accretion also possibly. These are from other folks, right? So I think there's a poster from Elbakian on disk instabilities, and Renee's talk yesterday, I think, was talking more about a smooth accretion process. I'm going to talk about instead asymmetric flows and dynamical interactions. So, okay, the asymmetric accretion flow case. I'm going to just stick with this example here. This is a pair of very high mass stars that are forming. So they're at least 20 solar masses, but they're still very clearly growing. W51, E2e, and North. In these cases, the mass of the envelope is much greater than the mass of the star. We have like a 200 solar mass core surrounding a 20 plus solar mass star. And there are outflows. So the outflows imply the presence of disks, I think. I see no other way to do that, but we can't see any rotation. There's just no sign of it. Now, the reason we don't see rotation is because it's optically thick. Even through ALMA bands, you see no sign. What I'm showing in these figures, the green is the continuum. So this is where the dust emission is. The red and blue are SIO, so tracing an outflow. And in both cases, what you see is what looks like accretion flows that are very non-axisymmetric, right? You have a triaxial symmetry of some sort on the left case and something that just, well, kind of the same thing in the right case. They look a little bit strange. And these are, getting very high resolution, as good as we can do with these really distant objects, where the resolution is say 200 AU. So there could be a disk hiding down below. This is the scale bar there is where we have an upper limit on the disk size because we can't see through that dust. But the point here is, okay, we have inflow coming from several directions. And when we look in more detail at the outflow from one of these objects, we can see that the accretion flow has been changing directions, like the net accretion flow onto whatever disk is launching the outflow has been changing directions over time. So this is the W51 North disk, and we can see there's an old outflow with a dynamical age of 300 years that is about 50 degrees misaligned from a younger outflow with a dynamical age of about 120 years. And the time to change that direction, so 50 degrees in projection is a very, very large change in the disk direction. During that time, if we go based on the amount of mass in the youngest outflow, it's something like a quarter to half a solar mass accreted in only about 100 years. But the average accretion rate is quite a bit lower than that. But so this is a case where you have asymmetric accretion flows dumping a lot of mass onto the stars very quickly out of a very rich envelope in a dense environment. So this is the case where it's still accreting, still growing. A different case is going to be, well, I'm going to talk about sort of the end state now. So when you start looking at high stellar densities, looking into clusters, and I'm now looking in the Orion Nebula cluster here, close encounters are frequent. So dynamical interactions happen all the time. So the left side is a plot from Andrew Winter showing the likelihood that any given star is going to have an interaction. So a neighbor come nearby over like a 1 megayear period, I believe is this plot. So at a density of 50,000 stars per cubic parsec, about half of all stars will have a neighbor come within, say, 50 AU sometime during that first megayear. Now, the Orion Nebula cluster and the Orion Molecular Cloud cluster are about an order of magnitude denser than that still. So they're very likely to have interactions. And here I'm showing a recent result from Justin Otter, where we observed the Orion Nebula cluster region, so actually centered on Orion source I, with almost long baselines. And we found actually several new sources. We found like 20 new objects. Every object we found is a disk-bearing source because it's ALMA. We can't see anything that doesn't have disks. And we actually found the density of sources is actually much higher, or well, not much higher. It's higher than we thought before, particularly in the OMC. The OMC, the central part there, is actually denser even than the ONC. So Orion Molecular Cloud cluster and Orion Nebula cluster. So there's an even denser spot where we expect dynamical interactions to be more important. And in fact, we know that there has been a really important dynamical interaction in the Orion source I, BN, and X interaction. So this is one possible end state to accretion where the stars get flung out of their parent cloud. So in this case, the left side here is showing an image from John Bally showing BN and where the vectors are showing the measured proper motions. So BN is moving one way, X is a low mass star moving another way, and source I is the third member of that triplet that also got ejected. And on the right is a diagram from Juan Farias. He did some dynamical modeling showing what masses of stars had to be involved in the interaction to fling them all out. And so the numbers that actually work are these red and green ones you might not be able to see, but basically Orion source I has to be 15 to 20 solar masses. And this is a case where, and source I is being flung out at about 10 kilometers per second. So this is sort of the poster case of where whatever accretion was ongoing can't be going on any longer because the stars are leaving. So we've had a closer look at source I, and we were able to measure the disk, the dynamics of the disk very directly, and determine that the central star is about 15 solar masses, so consistent with this three-body interaction. And so, source I is living right here at the center of the BNKL outflow. This is an image of the disk. And we learned some interesting things about this. So the idea with this model, with this ejection model, is that all of the material that had escape velocity less than the ejection velocity of the star was lost, right? And that ejection velocity is about 11.5 kilometers per second, which would be the escape velocity from a 15 solar mass star at a radius of 200 AU. So anything that was beyond 200 AU, it's left behind. It's no longer going with the star. One of the interesting features, though, this disk is directly aligned with the proper motion vector of the star, which suggests that the disk got launched out and it did drag along some material with it. Whatever material got dragged along, say it had a disk that was sitting around it before, now that disk is smaller and it's the angular momentum relative to the star changed when it got launched out. So now the disk is perfectly oriented in the direction of the star. But of course, we also have a pretty good upper limit on the disk mass. Now, the estimates of the disk mass, because it's an edge-on optically thick thing, are pretty coarse, anywhere from 0.02 to 2 solar masses. But even on that upper end, it's less than 15% of the stellar mass. So the total stellar mass is already decided at this point. This star is not going to grow anymore. And importantly, source I it's leaving its parent core. It is on its way out. It's not going to get any more material from the core. So this is one end state. But now I want to talk a little bit more about the mass of the disk and, the mass of the star and how we measured it. And this is kind of jumping topics entirely. This is an artist's illustration of source I, which, okay, great, it's an artist's illustration. But the reason we have this is because we found what I'm going to term binary disks. So this has nothing to do with binaries. It has to do with the fact that we have both salt and water in the disk. So salt and water is brine. And I am going to blame Adam Leroy for coming up with this term. He's the one who made that. So it's a different Adam. It's not me. Anyway, so the source I disk, as seen in salt, NaCl, is shown on the right. And so the radius of the disk is about 50 AU. We've seen this in now other sources. So this is G17. It's another disk. It's about 6 times more distant, so much coarser resolution, but roughly similar size. And there are some other detected ones that are a little bit less well resolved, so I'm not showing it here. So we found these weird molecules sitting in a handful of disks. And one thing that makes them useful is that these are the only molecules that directly trace the disk and nothing else around them. All the other molecules you see in these systems, like if you look at a hot core, you look at methanol, you look at formaldehyde, whatever, if it's embedded in a parent core, those other molecules also trace the core. These things are only traced in the disk, which means you can then use, you can use them to dynamically measure the disk mass. And so here, the red curves show a Keplerian curve for an edge-on 15 solar mass, or disk around a 15 solar mass central source. So that actually fits in the Orion case, which is on the left. And then in G17, the 15 solar mass case doesn't fit, right? There's material outside of that orbit. So you can say, okay, this is at least 30 to 40 solar masses, which is consistent with some other estimates. Also note that in source I, is that 2? Source I is really close by, so we could see one line pretty brightly. In the more distant objects, we can stack multiple lines. There are a lot of these lines per band in ALMA. So we found these about 2 years ago now, and we've been trying to follow up and figure out what exactly these lines are telling us, why are they there, what's special about them. Well, so one of the things we've done is start looking at other objects, and these are somewhat rare, right? So the first couple things, okay, I started with source I, it's the close one. The closest thing being weird being different is always a strange feature, but so it's the case. So we've looked at like 15 objects so far, and maybe 4 of them have these lines detected, and then 10 don't. And the 10 that don't tend to be the ones that are in richer sources. So the salt disks, the binary disks coincide with line poor sources, and I'll show you that in a moment. That implies that they're not really in hot cores. They're maybe they don't have much mass reservoir surrounding them. They're sort of already done accreting. And also in the 2 cases we resolved them, they seem to trace reasonably symmetric disks. So this is hinting that these disks might be something that trace the end state of accretion on high mass stars. And I wanted to show just one example here of what I mean by line poor and line rich. So the top example is G17. It it's actually got an ionizing photosphere. It has H30, it has recombination lines. Well, you can see there's this bright line here, that's water. And another bright line here is one of the salt lines. And some of these weaker ones, they're a little bit harder to see, but they're there. Some of them are there anyway, are the KCl, so other salt lines. By contrast, this bottom one here is one of these sources in W33. And what you should see is kind of the typical line forest that you see from a hot core. So it's very molecule rich. All these lines are not labeled. They're just like methanol, dimethyl ether, you know, all those sorts of typical hot core things. And the disk itself, I didn't show an image of it because it's just kind of messy. There's not that obvious a disk in this case. There's just a lot of stuff all around. So this is suggesting that when there's a lot more mass around, when there's more envelope, we're not seeing the salts appear. All right, so I'm actually gonna go into the summary here. I went nice and fast. So my argument is that ejection and dynamical interaction are particularly important in high mass star formation, and I'm going to have my literally bold and moderately supported claim that may be more important for stars gaining mass than disk-mediated accretion. We know that there are at least some cases where ejection is going to be the end state of accretion, and we have some pretty strong cases where dynamical interaction or non-axis symmetry are triggering bursts, and then we can use these binary disks that exist around some high mass young stellar objects to do a variety of things. So these are good for kinematic mass measurements. And I want to emphasize for a moment that these are going to be useful in the future because they are accessible well into the radio. So I pointed out early on that when you look at these high mass objects, they're very optically thick. Well, so if you want to get past that optical depth in dust, you need to go to longer wavelengths. And these lines do exist down to the lowest frequency line is 7 gigahertz. So this will be accessible to NGVLA in the future. Right now, the sensitivity is probably not there for VLA, but we're going to try. These may be tracing the end state of accretion, but it's kind of hard to say with such a small sample. We really don't have enough to draw conclusions. So there are more to be found, and I suggest next time you see a SALT proposal come by on your desk when you guys are all serving on the Alma TAC, give it a good read. Thanks.
Will there be any questions for them?
So source I has this pattern of SIO masers coming off, which made me think of like some cavity outflow, right? It's perpendicular to the disk, and that stuff has to be running into something, right? In order to, I mean, it has to be a lot of mass there in order to get the maser emission. And you shock excited or whatever you do. So do you envisage that there's kind of like a little bit of an envelope at 100 AU scales that's flying along with source I?
That's a good question. And I'm going to say no. I think the SIO masers, they're actually, so this illustration is kind of the right place to be looking at it, because what the blue haze here is supposed to show you sort of the salt ring. The SIO masers are coming from a region that's like a border. It's a border 100 AU out. There's SIO that's going way out, but the masers are quite close in.
Yes, but it's kind of very conical thing coming out, right? Yeah,
it looks like that. Just well, so your thing that you have to have an envelope to shape the cone,
and have stuff to run, for the flow or whatever's driving it to compress it.
So I had been thinking that was all coming from the disk, but maybe that's not that plausible scenario. But yeah, right. He's holding up the I think Gotti and others. Well,
this is Matthews. Anyway,
so
we should talk.
There is a parent. So source I is still actually in the parent core, but it's flying through it fast now. But I'm not convinced that there's not very much material immediately around it. But yeah, it's interesting to talk about that more. Sure.
Okay, we have Marina online.
More of a comment, but runaways can have a rather peculiar position on the HR diagram in that they sometimes can often be above all of the other sources in the cluster. That is to say, they probably have been ejected, and we're seeing them naked much younger than you would normally be able to see them otherwise.
Yeah, I don't really know where source X would lie. I don't think I and BN in this case really would land on an HR diagram in any useful way. But yeah, that's an interesting point. Thanks.
Okay, and lastly, a quick question from Hans.
Hello. Hi, Adam. Nice talk. My question is, how frequent are these asymmetric inflows? I mean, it could be that they are a good way of solving the angular momentum problem for high mass star formation, which is more dramatic than for low mass star formation, because after all, you have to get a lot of mass into a small volume and it has to lose angular momentum in the process. Could you comment on that?
I think it's a great question, and I don't have the data to handle that, to answer that. But I think, you know, if we get more ALMA long baseline data toward more high mass objects, we're going to start answering that question.
Okay, so we thank Adam again. Yeah. And then next we have Jörg Vink from ARMA Planetarium and Observatory talking about the accretion rate versus age and mass.
Yeah, so I haven't worked with Lee, unfortunately. There's still time, hopefully. But the whole idea of the accretion rate of the age from this 98 paper was one of the first things that I came across when I moved from m dot for stars in terms of winds. How do the wind masses rates depend on all the stellar parameters? And getting interested in how do stars accrete matter. So m dot again, I'm always interested in m dot. And the book that really inspired me was that of Lee Hartman. And I read about magnetospheric accretion, and I thought that's interesting, and maybe it can be applied to Herbig A stars as well. And I think that's very interesting. So if that's correct, then I'll take all the credit. And if it's all wrong, then I'll blame Lee, because I think, yeah, I think he already suggested that. So basically, normally, this is a very complicated picture, of course. So we don't really know where all the line emission comes from. We assume that all the H alpha comes from these accretion flows, but if that's really the case, I mean, obviously there will be a wind, and the disk itself might contribute, and there's all kinds of possibilities. So normally I say we need to look at more detail. We need to not just look at spectra, but we need to look also at the polarimetry, because then we get geometric information in addition to time information and velocity information. So today I say the exact opposite. I say we need less information, but we need to look at large samples, because basically we need to become a bit like extragalactic astronomers, ignore all the physics, and just look at what do the numbers give us if we make simplified assumptions. And for that, we can use large surveys like galactic plane surveys. And this is work from two former PhD students, started with Geert Barendsen with IFAS. I'll tell about that in a second. And it was continued with Venu Kalari, who's still working on these mass accretion rates from photometry. So that is what I want to talk about. And there had to be some reason. Does this work? The middle? Oh, great. Yes. So so my interest really is in the circumstellar medium around all kinds of stars. So what I'm always thinking of is that for T Tauri stars, it's really the magnetic fields that play the dynamical role in the CSM. And for early type stars, it's radiation pressure. And then the Herbig stars are the nice ones in the middle, where we don't really know which one it is. And we heard a talk by René yesterday, so I'm not going to really talk about that. But when I first made these plots 15 years ago, we thought the O stars were the most massive ones. But we now know there are stars that are super O stars on steroids, 150 to up to 300 solar masses. And it's a big question of how those stars form. I would even argue that those stars might be even more massive. So even if you look at the most massive stars we know of, after about 1.5 million, and you have masses of 200, 300 solar masses, I've actually shown that because of the way the mass loss rate does also not just depend on luminosity, but also mass, and it's really the specifics of how things vary with all the different stellar parameters, that we can actually claim that the mass loss rate may be so high that you would have started with 1,000 solar mass star. We cannot know if those stars were 1,000 solar mass star or only 300 solar mass stars. And these things will vary with metallicity. And it also depends a lot on the mass accretion rate, because in this case, of course, the assumption is that the mass loss rates go up to 10 to the minus 3 solar masses per year. So if the mass accretion rate is of a similar order of magnitude, then that will set an upper limit. So I think in the star formation community, people usually think of that it's radiation pressure on dust that sets the upper mass limit, but I would argue it is the radiation pressure on gas. So we really need to look at the inner few stellar radii, where all the gas opacity plays a role, and really look at both the inner regions for mass accretion and for mass outflow in terms of the what sets the mass limit. So now people have speculated that maybe mass accretion rates depend on metallicity. There's a couple of papers from Demarchi et al. That claim there is a metallicity dependence, that the mass accretion rates of T-Tauri stars in their clouds are higher than in the galaxy. Some people have maybe some problems with the method of photometric H-alpha, but that is not really, I don't think, the issue. But when we did a spectroscopic study of a galactic region in our own Milky Way, so much closer distance, and we compared the mass accretion rates with Orion, we don't find any difference. So I don't think there's evidence for metallicity dependent mass accretion rates. So we need to understand what is going on with the different prescriptions of mass accretion rates on stellar parameters, and especially what are the biases? Because if you look in the Large Magellan Cloud, you look at 50, 60 kiloparsecs, you probably miss the lower mass accretion rates, I would say. So you really need to look at how these things vary, not just in one dimension, but on all dimensions. Now, and I would say that a very good way of doing that is using the large photometric surveys. So IFAS is one of them. It's the INT photometric H-alpha survey. Goes down to RF20. So this is around the galactic plane, 5 degrees either side, and it's the entire northern galactic plane that is now mapped, well, in the first instance in just RI and H-alpha, but it's now been extended. But we started off with just RI and H-alpha. You think, what can you do with that? Well, quite a lot, actually, because, well, of course, one thing you can do is make beautiful pictures. It's amazing, and if you want to know more, look at Nick Wright's website. He has lots of beautiful pictures. And we can start searching for T-Tauri stars by the telltale H-alpha emission, and then we can measure mass accretion rates. And how do we do that? Normally, people would think, well, you do that from the H-alpha emission. So if you're a strong emitting star, you would have a very strong H-alpha emission, and for weak-line T-Tauri stars, there's hardly any emission at all. And what I would say is you can look at these very narrow emission lines to get these mass accretion rates. And the method really relies on this kind of diagram where you have broadband colors on one axis. So basically that's like an effective temperature. And then here you have your excess of your H-alpha. And you can show that this is just some synthetic spectra and so on, that the R minus H-alpha can be converted into H-alpha equivalent width. And we've done some tests, and then indeed the weak-line T-Tauri stars fall between up to about minus 10 angstroms, and the classical T-Tauri stars are above it. So not only can you find the T-Tauri stars, you can also measure the H-alpha line emission. And we have benchmarked this against spectroscopy. So we looked at a region like IC 3096 where spectra were available. And we can plot the H-alpha equivalent width from photometry, and the two agree. Now there's some scatter, but it can be applied. And that is very helpful because this is a way to do large samples. So obviously, the H-alpha will, I just show this plot as many times as possible to get Carlo screaming many times, basically. So this has not been shown yet. This is the way that normally these mass accretion rates are determined. From the accretion luminosity. Also, I just wanted to point out that this Rn is usually assumed to be 5 stellar radii, but we can measure this. There are ways of measuring this. We don't just need to rely on dipole field strength estimates, but from spectropolarimetry and so on, we can measure this. Anyway, when we plot these mass accretion rates versus mass, when we first did this, you can see that we found an m.m relation that wasn't as steep as normally found from spectroscopic surveys. Normally it is about quadratic in mass, and we found it to be more linear. but we were quite happy that we had a very good handle on selection effects. And we know our detection limits much better than in many other surveys. So that is quite steep, and not so steep at all, but maybe that's quite a surprise to some people. Another question, of course, is why are there such large scatters? Why is there such a spread? Now, one way you could get a spread is from the fact that in reality, of course, you have rotational modulation. These accreting columns, they are not constant. When you look at a certain angle, you will see a certain accreting columns come in and out of the line of sight. So you expect to measure a variation. And just because the H-alpha varies doesn't mean that the mass accretion rate itself varies. It just means that your information varies. But if you look at what we found in this paper with Costigan, it is about 0.4 dex. So that is not enough to explain the huge spread, of course. So there are other things going on that we need to understand better. So things are maybe not just a function of mass, but also a function of other parameters like time, as discussed by Renee also yesterday. Now we did another study, and interestingly, here we found m dot goes with m to the 3. So there's quite a lot of spread, and it depends a bit of also in the mass range you're working. So these issues are, I don't think, very well resolved yet. And if you combine the two, we find actually very similar results as the spectroscopic plot. So basically, we've learned that 1 plus 3 divided by 2 is 2, because this is more or less quadratic. So my point is, it agrees with spectroscopy. So we can use this now for much larger samples, because we have now the entire galactic plane inside with many young clusters where we can apply this. And if we do that for m dot versus time, we get a very similar plot, goes to the -1. Now, whether that agrees with the viscous models, that remains to be seen. But this is the kind of work we can now do with large samples and actually see how the mass accretion rate, basically how age comes into this. Now the ages, of course, are a bit of a problem, as I've already discussed in this meeting. But I think we get much more handle on that with Gaia and so on. We will now have many different ways of getting much better ages. So I also wanted to say that is no longer only used for the H-alpha. The H-alpha, we think, arrives from these accretion columns, but then it shocks on the stellar surface and you get U-band emission. So we now have also U-band photometry from VFAS plus. The plus stands for the U-band. And if you plot the mass accretion rates from H-alpha versus the U-band, you get a good correlation as well. Now, that's great, because originally, of course, the H-alpha was benchmarked against the U-band. So it is good that this works, but it does. So I really think we're in business now to apply this really to the entire galactic plane. So with another survey, UVEX, also on the INT, these two have been combined. We now have hundreds of millions of sources to search for new Tauri stars and measure their mass accretion rates. And you can do exactly the same thing on the south with VFAS. And the same regions will also in the future be mapped with spectroscopy, so then we can actually compare again whether the photometric methods and the spectroscopic ones agree. So what do I think we need to do? We need to really apply this method, and this is really the main point that I want to make, to get uniform samples, so that at least the problem that I sometimes see is that people study one region, apply one set of isochrones, apply one set of methodology. Other people look at another region, do the same thing. How can we really compare all these different regions and the physics going on, all these different clusters and so on? And what happens in between the clusters? I mean, sometimes you have a cluster here, you have a cluster here, but what about in between? Is there no Tauri stars there? Well, I think we just haven't found them because no one's looking there because, well, you first need a nice nebula to say, hey, there's something happening there. Let's do a spectroscopic survey. So here we can do this really across the entire galactic plane, compare with other large surveys like UKITS and other infrared surveys. We can really do this statistical so that we get consistent ages out. So I would say this is something that needs to be done now, because I think in the future, we really want to do the more, what to say, much more detailed studies with polarimetry. But I think that will really come to fruition when we have much larger telescopes, because you really need 40-meter telescopes to get proper polarimetry. And then we can really map the accretion, just like we can map magnetic fields with Stokes V spectropolarimetry. We can map the gas with Stokes QU spectropolarimetry, but you need time and you need, you really want to do this with larger telescopes. So I would say, in the meantime, right now, especially people who are interested in data mining and who are really interested in large samples and so on, there's a huge databases available to measure mass accretion rates and to really study these things consistently. So I hope that it will inspire some people to do that. All right, that's more or less what I want to say.
So Nuria?
That's a great idea, but what worries me is like the use of the equivalent width, because essentially like what matters is the flux of H alpha, right? So of course, like the lower masses, like M stars, right, for the same flux, you will have a larger equivalent width that you would have if you have a G star. Right, so in other words, like the limiting thing of equivalent width between weak Titori stars and classical Titori stars is not always 10. So, I mean, if you actually, if that's the case, then I think like your M stars will have lower M dots that you get, and the higher mass stars will have higher M dots that you get, which actually would steepen like the slope. So I don't know if you could do some kind of color correction or something for the spectral type.
Yeah, no, I'm also not denying that one should only do this and forget about actual. It shouldn't replace actual spectroscopic modeling, but I think the two can really benefit from each other by benchmarking and cross calibration, because I think, I think you need both. That's basically what I'm trying to say. But I do think we need much larger samples to address some of these questions, because what I'm talking about is not another 100 stars. I'm talking about tens of thousands.
I understand. Yeah. No, and it's great, right? But I'm sorry, if you, I'm thinking that maybe you could add an additional prior, something that has to do with somehow tell you something about the spectral type of the star, so you could actually tell your criteria, you know, refine your criteria.
Yeah.
Okay, and Patrick, quick.
Thank you. Can you show us again this plot when you have the accretion rate as a function of time? Because what I find intriguing is that so this plot starts typically at 10 to the 5 years, meaning that at this stage you are still at the class 1 stage. Okay, and in the class 1 stage, I would argue that the environment is largely controlling the accretions you have onto the disk/stars. And what I find intriguing is that you have a continuity, okay, you have a single slope, more or less, with maybe some little more dispersion. So this, to me, strongly asks the questions whether we don't have a continuous process, and which would mean that the environment should be playing a role. It's not the disk in isolation that would control the accretions. Okay, otherwise you would see a break.
Yeah, just two comments. One is I wouldn't take those ages seriously. I mean, these, no, sorry, they come from isochrones. And I think, we have to be careful. Sort of in this regime between 6 and 7, so between 1 and 10 million years, I think they're, you can, more or less. I mean, there might still be errors, but you can kind of, a 3 million year star is not 300,000 years. But when we get to 100,000 years, I don't think we can measure that at this point. But I agree that it would be very important to start looking more also at not just what happens in the pre-med sequence, but in earlier phases and how these things combine. So I think going into near infrared and then further to actually probe
in a more consistent way how the mass accretion varies with time from earlier on. That would be very interesting.
Okay, so we can thank Jarek again. Okay, so we have our final talk before the coffee break. So we have Manuel Ganji from the INAF in Rome, and is going to talk about the GHOST project, accretion properties in the Taurus Auriga region.
So hello everybody, thanks to the organizer for giving me the opportunity to participate in this meeting. And in this talk, I would like to introduce the GHOST project, and in particular the latest results regarding the measurement of accretion properties in a sample of classical T-Tauri stars in the Taurus Auriga star-forming region. The project is led by Simone Antonucci from the INAF Astronomical Observatory of Rome. We start with the problem of disk evolution. We know that disk evolution is a complex process which occurs in time scale of 10 megayear, where different mechanisms give a different contribution to the dissipation and to the clearing mechanism of the disk, from mass accretion to the mass ejection, from jets, winds, photoevaporation, and formation of planets. So reliable measurements of the parameters characterizing such processes are then essential to provide important constraints to the different disk evolutionary models. From an observational point of view, we can obtain a wealth of information with the use of high or medium spectral resolution spectra in a wide coverage in wavelength from the ultraviolet to the near infrared, because in this way we can have different spectral diagnostics, so we can have a complete picture of the different processes occurring at this time of stellar evolution. In this context, we started with the GHOST project, which aims to carry out a first systematic optical and near-infrared survey of the Taurus stars in the Taurus star-forming region. With the use of a wide spectral coverage, and this allows us to remove systematics due to the variability facts, for example, and to use multiple tracers, and with the use of a high spectral resolution, which allows us to have detailed information on the morphology of specific line profiles. We use the JARPS spectrograph. It is an instrument located at the Telescopio Nazionale Galileo, and it combines two different spectrographs, the ARPS node, which operates in the visible range, and the JANO spectrograph in the near infrared. The ultimate goal of the project is to provide, to measure stellar properties, mass accretion and mass loss rates in an homogeneous and self-consistent way, to put them in relation with the properties of the overall disk structure coming from the HALMA observations, and then to provide a solid observational reference for the disk evolutionary models. In addition, our spectra are flux calibrated. This is done thanks to different ancillary observations made with different facilities, close in time with the JARPS observation to avoid possible effect of variability. And we take photometry in the visible and in the near infrared, but also low resolution spectroscopy in the visible, and for some sources also in the near infrared, to get a proper flux calibration of our spectra. The sample was selected based on the census by ESPN 2014 and was mainly driven by the JARPS sensitivity. We made a cut in the magnitude, in the J and the R magnitude, and this allows us to observe sources with mass greater than about 0.3 solar mass. We have already observed 50 sources between 2015 and 2020. 41 of them are classified as class 2. In addition, as Reggie mentioned, the majority of our sources have been already observed with HALMA, so their disks were spatially resolved. And more than half of our sources have present a full disk, but we also distinguish between a transitional disk and disk with substructures, so disk with inner hole, gaps, ring, etc. The observing program was structured to have for each semester a specific subsample of sources suitable for specific scientific purpose. We started during the science verification of the instruments presenting the disk properties of two of our sources. Then with a higher number of sources, we perform a study of the atomic jets through a study with the forbidden emission lines. Then we connect the atomic and molecular disk width component for a comparison between the hydrogen molecule line in the near infrared and the oxygen line in the optical range. And we have recently published a work where we present a pilot study of stellar accretion properties, where we present the overall methodology that we adopt to measure the stellar properties and the accretion parameters of our stars. Today, we are ready to present a first preview of the measurement of the accretion properties of the whole ghost sample. The method used to measure the stellar properties is summarized here, but you can refer to our pilot study for any details. Basically, the stellar parameters and the optical veiling as a function of the wavelength were retrieved using the optical spectrum with the Rothfield code. The visual extinction was determined with a comparison with the non-accreting templates with the negligible extinction that were artificially rendered to match the observed spectra. And finally, the luminosity and mass were determined with a proper integration of bit set of models and with the use of primitive sequence evolutionary tracks. The accretion parameters were derived by looking at multiple permitted emission lines. In particular, we use the empirical relationships between the accretion luminosity and the line luminosity. And here I show just an example of what we have done for one of our sources. So here I plot the accretion luminosity as a function of the line luminosity. We use a maximum number of 21 lines from the blue to the near infrared, and this allows us to significantly reduce the error in the estimation of the accretion luminosity. That is, its measurement is represented by the median value of such a distribution. Here I present the first result, the well-known plot of the accretion luminosity as a function of stellar luminosity of our sample compared with the sample of the Lupus and Chameleon that were already studied with the X-ray survey by Carlo Monara and Juan Alcala. We note an overall similarity between the three distributions. And regarding the disk classification, we note that the transitional sources here displayed in green dots always fill the lower region of such diagram, the region below the boundary where the accretion luminosity is equal to 0.1 stellar luminosity, while full sources show the largest spread in both the directions. We have too little statistics to say something about any particular trends regarding the disk with the substructures. Here I show the diagram of mass accretion rate as a function of stellar mass. As already anticipated, due to the cutting in magnitude, we are not able to observe sources with low mass. So we are not able to recognize in our distribution the possible double power law that was theoretically predicted and was suggested for the distribution of the Lupus Chameleon. But again, if we restricted ourselves in the high mass region, we can see that there is an overall similarity between the three distributions. Again, transitional sources tend to have lower value of mass accretion rate, while no particular trend between full disks and disk with substructures is seen in this diagram. So let's try to connect the accretion properties with the jets properties. This latter can be retrieved by looking at specific lines in emission. In particular, one of the most studied, most brightest is represented by the oxygen 1 line at 630 nanometer. And this line usually presents a complex composite profile made of one or more than one low velocity component that are characteristics of these twins, and the high velocity component which directly trace the jets. It has been already shown that the luminosity of such component well correlates with the accretion luminosity. And this suggests that the origin of such components is somehow related with the accretion mechanism. And in addition, for the first time, Banzatti have found that also the projected high velocity centroid component, so the velocity of the jet, correlates with the accretion luminosity. We repeated this kind of analysis with our data, and we found a similar dependence between the projected high velocity component and the accretion luminosity compared with the distribution of Banzatti. Our trend has a lower dispersion that maybe thanks to the homogeneity of our data and to the simultaneous measurement of the projected high velocity component. So in this case, we are not including possible effects of variability that may give a contribution in the dispersion of such kind of relationships. Two explanations can be at the basis of such trend. The first one, we already know that the mass accretion rate and hence the accretion luminosity is proportional to the mass loss from the jets. So in this case, we have a direct link between the accretion luminosity and the velocity of the jet. But from another point of view, we know that from MHD models that the velocity of jets is proportional to the stellar mass, to the square root of the stellar mass. So in that case, such correlation would be just an indirect correlation due to the fact that both the velocity of the jet and the mass accretion correlates with the stellar mass. Finally, I present another diagram where I compare the mass accretion rate and the disk mass. We already know that for the loops at a million, there is a moderate correlation between these two quantities. And we find a similar dependence in our data, a low or moderate correlation between the mass accretion rate and the mass of the disk. In that case, I'm considering now here just the dust component of the disk mass computed from the millimeter fluxes measured by ALMA. And regarding the disk classification, here we don't find any particular trend between full transitional disks and disks with substructure. So, in summary, within the GHOST project, we are able to measure in a self-consistent way and in a homogeneous way not only the stellar parameters, but also the accretion properties. We have found that the accretion luminosity and the mass accretion rate are comparable with those obtained in the Creminion and Lupus forming region that are similar in age with the Tausoliga region. In addition, thanks to the ALMA data, the GHOST plus ALMA data, allow us to directly put in relation such properties with the disk characteristics. This allows us to have a better picture of the processes occurring in these sources. We have found that the transitional disk sources have in general lower values of accretion, and this might be compatible with the evolutionary status of such sources, while no particular trends seen between full and disks with substructure. But we need more statistics, especially for disks with substructures, to draw any firm conclusion on it. In addition, we also find a correlation between accretion and jets, and this opens new questions regarding the physical origin mechanisms that are at the basis of the jets and their correlation with the accretion. As a future perspectives, we continue the GHOST program. We start a monitoring of some selected sources to evaluate the variability of mass accretion and mass loss. So this will be done in synergy with the Ulysses Odysseus legacy program. So we also have HCT spectra and with the Penelope program. This way we can have more information with the use of different spectral ranges. I thank you for your attention.
Thank you very much. So we have any questions in the room? Yeah, any online? Okay. So maybe I can ask you a quick question. So where you were showing the forbidden emission line profiles, the oxygen one, and you talk about the correlation with the high velocity component and the accretion. Did you do something similar for the low velocity component? Were you ever able to measure an outflow rate for that component, or?
Actually, no, but we can do that, of course.
Okay. So yes, so I was wondering as well, I know a lot of this work was already done with X-Shooter by Carlo and Juan, and so what is the difference here with this instrument? Is it just you can get more data? Is it better spectral resolution than what they had with X-Shooter?
So the mainly difference is the spectral resolution, of course, and also the spectral extension. Our spectral extension is less than of the X-Shooter spectra, but also the methodology with the high resolution we can use multiple lines to do this kind of measurements. Actually, also with the X-Shooter spectra, but the main difference is just the resolution. Yes.
Okay. Okay. Thank you.
Thank you.
Yeah, you have a question?
Hey, hello. Yes, I have a question. My name is Robin Mental. I'm a PhD student at UCD, working with Rebecca Garcia Lopez on also with, and we have a JARBS survey on 25 fabric stars. And I was just wondering, I don't know much about Titaurus, but do you have found any interesting signatures or emission profiles in the hydrogen recombination lines of the survey? Because we have found a lot of interesting signatures in our survey, and I was wondering what you have found in your survey.
Yes, of course, we have a lot of emission signatures in our sample that are clearly visible, especially thanks to the high resolution of our spectra.
Okay, and other like double peak Kaplan style, or what kind of, or do you just have like simple emission and accretion?
Okay, yes, the morphological analysis of such profiles is still under analysis. Of course, in some cases we have some evidence of double peak, but it's not so common among our sources. But this kind of studies still under analysis.
Okay, it's interesting. I would like to have a chat with you about this double peaks, because I'm pretty much working on this exact thing. But thank you for your answers.
Okay, thank you. Thank you.
So thank you, Manuela, and I think we'll just thank all the speakers from this session. Okay, so we'll start then the final part of this session 4. We have an invited talk from Rebecca Garcia Lopez from University College Dublin, talking about the inner regions of protoplanetary disks and the work that she's done with interferometry.
Okay, thank you very much, Emma. I'm going to start. So when I have these presentations, I usually start justifying why I want to study the inner disk. But I have decided that this time I'm not going to do that. I'm just going to tell you that I'm going to talk to you about the inner disk because it's what I like to do. And I hope that most of you will love to know more about the inner disk as well. So I'm not going to talk about the structures, planets, and so on. But in any case, so this is what I love to do, because here happens a lot of interesting stuff like the accretion, the winds, and so on. There is only a small problem about the inner disk, and it's that it's very small. So it is very difficult to observe it. And because of that, what we use, or what I'm using to try to understand what are the physical processes and linking some lines with some physical processes, is to use optical interferometry. And I'm very sorry to tell you that as far as I can tell you, this is not possible to do with ALMA, at least not yet. And so for this talk, I'm going to use data taken with gravity. And gravity is the second generation of beam combiner for the VLTI, and it operates in the K-band. And it can join the light of up to 4 of telescopes. So 4 of the 8-meter duty telescopes, so 4 of the 1.8 auxiliary telescopes. And most of the data that I'm going to show you here, they have been taken with the small telescopes for the case of the air-big stars, and the big telescope for the T-Tauri sources. So this is an effort that the YSO group, having granted time observation time of gravity, has been doing for quite some time now. And in this talk, I'm going to talk to you only about our line program. So I'm going to talk to you about gas and the gaseous disk. And I'm going to use some lines or trying to trace some of this gas using the Bragg gamma and the CO. And then I'm going to try to briefly discuss about our imaging program and what we are doing with optical interferometry about that. So why these lines? Well, the Bragg gamma line is a little bit complicated because we are not really sure where it comes from. So we can trace almost everything in the inner disk, from the gaseous disk itself to the accretion processes, winds, photoevaporative winds, everything that happens in the inner disk. Then we also use the CO because now we are able to detect it using optical interferometry. As a tracer of the warm gas component of the inner disk. So when I'm talking about the inner disk, I'm just talking about the dust-free disk, so no gas. And here I wanted to show you some of our results about the CO. So this is one example for one of our air-bigs. So this is 51 off, it's a very luminous star. And you see that we can detect very clearly 4 bunkheads, even perhaps 5. And we can detect these small signal here that are visibilities. So the visibilities give you an idea of the size of the objects. When they increase, and here they increase a little bit, even if tiny, what it means is that this emitting region is smaller. So the gas emitting the CO is smaller than the surrounding continuum. So what it means is that the CO is being emitted within the dust-free disk. So it comes only from within the gaseous disk. And then you can see also that we detect these signals here, that they have this S shape. They are differential phases, and they give you the photocenter of the line with respect to the continuum. When you see these characteristic S shape profiles in a differential phase, you tend to think that you have something rotating around, so maybe encloperian rotation. So in order to interpret our data, we use a simple CO ring model in LTE, encloperian rotation. And we try to reproduce the spectra, the visibilities, and the differential phases. Here I would like to make emphasis and that we do not have any detailed model of the region. So meaning we do not have a detailed model of the gaseous disk without dust. And the main work that there is available comes from Muzzerole from 2004, and is just based on simple accretion disk models. And he used mean opacities in LTE. And this is probably not the best approximation for the disk atmosphere, especially around these big K stars. They also predict a forest of molecules. And as you know, many of you know, it is very hard to detect these molecules in the inner regions of disks. But nevertheless, so using this simple model, we were able to reproduce our observations, and what we found, and the alpha size for the emitting region, and what we found is that the CO comes from a very really tiny region within the disk at a distance of only 0.1 AU, so really, really close to the star. The gas is very warm and is also very dense. So I gave you this example, and we have similar results for other airbics. And also what we are going to do, or what we are trying to do, is to extend these results also to high mass YSOs. And here I'm showing you some example from a paper of Alessio, where he detected CO also in one of the high mass YSOs. So here you can see the rovibrational CO band. And then you can see also that it has visibilities and differential phase signature. So meaning that, again, the CO, even in this high mass YSO, comes from the inner gaseous disk. So without the dust sublimation radius. So you see, this is the size of the K-band continuum emission, and this is the size of the CO. So it is well within the dust sublimation radius. And in the case of the high mass YSOs, this is very useful, because if you assume that the CO is rotating at Keplerian velocity and you're able to fit that, then you can derive or give a very accurate measurement of the mass of the central object. And for this object, it's very important, because many times we do not know the spectral type. So we do not have a very accurate measurement of the mass for these objects. Regarding the bracket gamma line, here I'm going to show you our results on the Erbic sample. This is because the Erbics are the brightest sources in our sample, and so it's for the ones that we have more data at the moment. But we are working on the T Tauri sample. And for the Erbic, we have a sample of 26 stars, and that are the same as the sample that we published for the continuum study. Of these 26, 22 of them show bracket gamma line in emission, but only 16 out of 26 have a bracket gamma line that is above 10% of the continuum level. And we decided that we are not going to study sources of the bracket gamma emission for sources with bracket gamma signals lower than this, because then the percentages are very large. So the idea with this study is to try to understand where the bracket gamma line comes from and what is tracing. So here I just wanted to show you an example of some of our data. So for most of our targets, the bracket gamma is single peaked. Also because gravity has a tiny spectral resolution, 4000. But for some of our sources, we see that the bracket gamma line is double peaked. Of course, when we do our analysis of the data, we remove the photospheric absorption feature to have just the pure emission on the line. And just as an example, what you can see for all of our sources is that the visibilities, we have visibility signals across the bracket gamma line. The visibility gain increase, meaning that the bracket gamma is being emitted within the dust sublimation radius. And sometimes we also have beautiful differential phases. And on average, as I said, for all the sources, what we have is that the bracket gamma is located within the dust sublimation radius. And when we do our analysis, and I can tell you more in detail if somebody wants to know how we do that, we subtract or we remove the continuum contribution from the line and from the visibilities and also from the differential phases, and then we analyze the continuum subtracted bracket gamma line. And we do fittings on the visibilities to derive a characteristic size of the line. And what we can find is that we have a component that is resolved in most of our objects, but we also have a component that is unresolved. At the spatial resolution of gravity, we have baselines up to 130 meters. So this is to make it more clearly, so to visualize it more clearly for our sample. And what we see is that we have this resolved component that it has an average value on size of around 20 stellar radii. And we have this unresolved component, unresolved for our gravity longest baselines of that 130 meters. So that means that the smallest that we can go is around 5 stellar radii. And if we then try to understand what is this resolved component that I call resolved component, we try to compare this with different characteristic sizes. For instance, I compared it with the location of the co-rotation radius of the sources. And what we find is that the bracket gamma is larger than the co-rotation radius by between 6 and 8 times larger than the co-rotation radius on average. So that made us thought that it could be tracing some sort of winds, perhaps a photoevaporative wind. So then we went and tried to investigate whether a photoevaporative wind could be causing this resolve component. And we found these papers, or actually the Protostar and Planet 6 review by Alexander. And if you look into that, what you find is that the bracket gamma line emission is smaller than this so-called gravitational radius. So this is the radius at which the peak of a photoevaporative wind will peak. And from this paper, so what it says is that if you have a photoevaporative wind, this the mass loss rate will peak at around 0.2, 0.5 gravitational radius. And what you can see is that for all our sources, the resolve component is smaller than this value. So that makes us think that it's difficult that this resolve component comes from a photoevaporative wind. So what is left? So what we have left is the perhaps an internal MHD wind in these sources, or perhaps the surfaces of the disk itself. It might be that. We cannot exclude, of course, that the unresolved component come from some sort of magnetospheric accretion, in particular for the A-type stars, or perhaps some boundary layer accretion. That we cannot say more because we are not resolving that emission. But the resolved emission comes from something that is bigger than accretion, so it cannot be accretion, and it's very unlikely that it is a photoevaporative wind. So what can we do in order to try to further constrain the origin of this line? We can look at the differential phases, and sorry for the small dots here, and try to see whether these differential phases trace give us some information. So these differential phases is like if you are doing a spectrometry, for those of you that are familiar with spectrometry. And what you see is that the shape, so if you put the radial velocity versus the position, so the displacement of the line, you see that in most cases we have this, again, this S-shaped profiles, so nothing really shocking. Perhaps you have some of them that do not follow really an S shape, but again, the resolution is 4000, so there is nothing really striking that make us think that this bracket gamma is not consistent with something rotating in Keplerian rotation. And furthermore, from these differential phases, you can also get a good estimate of the inclination and the position angle, and in general, these displacements so agrees with the fact that the gas has the same inclination and same position angle as the continuum emission. So it is not clear how to distinguish between the base of that disk wind that will rotate at Keplerian rotation and the disk itself. So that's tricky, and we need more data and more spectral resolution, I would say. So in order to keep looking into that, what we have done is to try to combine our observations, interferometric observations, with high spectral resolution. So we have a program like the one that they just have presented with from Rome with Hubs and Jano. So Jano gets up to 50,000 resolution at the near infrared, and Hubs observe a 100,000 resolution in the optical. So we have simultaneous spectra from the optical to, so from around 4,000 angstrom to 2.5 microns. Simultaneous observations of the Erbic sample, and I just invite you to go and take a look to Robin's poster outside, where he analyzed one of the Erbics. But again, so with this spectral resolution, sometimes we see these double peak profiles even in the bracket lines, and they are consistent with a disk in Keplerian rotation, at least for this case. We are still analyzing the full sample. Another thing that we are trying to do is to try to obtain images of the brachiogamma line, so reconstruct interferometric images with gravity. And this is the work of Youssef here, for instance. So this is one Arabic again, and he has been able to reconstruct the brachiogamma line image using gravity data with the small AT telescope. So this is the image of the brachiogamma. It has a very tiny size, again, always within the continuum. So within the dust sublimation radius, it has a size of around 0.3 AU. And again, in this source, the image tells you, and here you can see the GIF with the Keplerian rotation pattern. So the brachiogamma moving consistent with a Keplerian rotation pattern. But not all the stars are so complicated as the Arabic, and many T-Tauri sources are also very complicated, I have to say. And in our sample, we have TW Hydra, and in this case, the things got simpler because it's a cleaner data set. So you all know TW Hydra, so it's the prototype of the transitional disks. It has a dust depleted inner cavity of around 1 AU, and it also has an evidence of photoevaporation. So it is a nice target to try to observe with gravity. It is also face on, that's very important. So we went and we observed TW Hydra with gravity, and these are our results. So we detected the brachiogamma line because TW Hydra is still accreting. It has a very small accretion rate, but there is still gas falling into the star. And then we saw these visibility signals within the line. So here you see that the visibility dropped, but in this case, what it means is that the gas emitting the line is bigger than the continuum source. In this case, because TW Hydra doesn't have much excess, the continuum is the star. So the brachiogamma line is bigger than the star itself. So that's a good starting point. And then we subtracted the continuum from the visibilities, and we did our geometrical fitting. So we assumed that we have a star, a disk, emitting in continuum and the line. And what we found is that the line comes from a very small region of around 4.5 solar radii. Oh, I went the other way around. So if you translate that into stellar radii, it is very small. It's around 3.5 stellar radii. So I was very surprised about this because I was sure I was looking at the photoevaporative wind of TW Hydra at the time. Then when I translated that into a stellar radii, I said, this is not the photoevaporation. So let's check whether we are really seeing insights and we are seeing the accretion. So, we think that this is not due to the MHD wind of the photoevaporative wind, apart from the size, is because TW Hydra, when you look at the forbidden oxygen 1, for instance, it doesn't have a broad component as the one that they have shown us before. It only have a narrow component, meaning that this is it doesn't have an MHD wind or any evidence of it. So then, because it is TW Hydra and it is a very well-studied source, we were fortunate enough that there are very detailed studies about the magnetic field in TW Hydra. So we know that TW Hydra has a magnetic field that is mostly dipolar and it's very strong. And the dipolar component is between 400 and 700 Gauss in this source. So if from that magnetic field measurement, you estimate what is the size of the truncation radius estimated for the source, you derive that this is between 3 and 4 stellar radii. And this is between 4 and 5 solar radii. And this is exactly what we found for the size of the line. So we said this has to be a magnetospheric accretion. So we are tracing, so the brachiogamma is tracing somehow the gas that is falling into the star. So it might be that we are tracing a gas across or along an accretion column. So this was our conclusion, and we were very happy to observe TW height and being able to finally get a strong proof of the magnetospheric accretion process. I have to say that there is more work going on this. So, for instance, you can check the work of Jérôme, of the group of Jérôme Bouvier, that they are also using gravity in other sources, in other theta resources, combined with SPIDU observations and high spectral resolution observations in order to do the same work. So like the work we did for TW Hydra and extend it to other sources. So I'm sure that in the future we will be able to get more measurements, more proofs that the magnetospheric accretion is there. And just to finish, I want you to show the final result about the magnetospheric accretion, so that even now we are even able to get more details about how magnetospheric accretion works, and how and there is this new paper in Nature that I only read a couple of days ago, where they compared test observations, photometric observations, with modeling of a hot spot, and they are able to infer or to suggest the presence of a radial density gradient in the hot spot. So we are even getting to this point where we are able to get these nice observations. So, and this is my final slide, and I will finish here. Thank you. Very fast.
Great, thank you, Rebecca. So do we have any questions in the room? In Nuria?
Want to say that when you say that these are the model Montserrat et al. 2004 in a disk, it's very simple. It's not that simple.
No, it's not that simple.
It's not that simple, right? I mean, because it was a full solution, self-consistent solution of the heating and the vertical structure. The thing that we didn't do there, or it was the D'Alessio model, was that it wasn't taken, we didn't take into account the actual heat. We assumed that it was just heating by the star and not like the UV, that taking into account the actual gas heating sources.
Yes.
And if we actually do that, probably one could get in the upper layers temperatures up to 10,000 that maybe could actually explain those hydrogen lines. So that has to be done.
Yes.
But probably those
I
data
meant,
of yours are great for that.
Yes, what I meant is that we need more work done on the inner disk. Yes.
Very nice talk, Rebecca. Can I ask you about the asymmetries that Jérôme is finding in the positional offsets, the back gamma line? Is that due to the fact that, I mean, if we are tracing accretion there, that there may well be asymmetries in that accretion?
Yes, there might be. Yes, there might be.
That's possibly the origin of that, in which case one should look at it perhaps over time as well and see what's happening.
Yes, that's something that we can do. But as if you know me and you know us, we are very pessimistic. So we have to be very, very, very sure that the displacements and the movements and this difference in the peaks of the visibilities and so on, they are real. So
but it's the right sort of scale.
Yes, yes, it is. Yes.
Great.
So in principle, yes.
Thank you. We also have a few questions from Zoom. The first one is from Michael, if he wants to unmute.
Thanks, Rebecca. That was extraordinary to see these new data. Can you comment on the CO to H2 ratio, whether you've compared it to what you'd expect in the sources that you looked at? I'm wondering about the column density you mentioned, that it was very high, and whether you see an enhancement of CO relative to what you'd expect.
No, we cannot sell anything like that without a proper modeling, I guess. Where the densities that I'm giving you are CO densities. We just assume a CO over total gas density of, I forgot what it is, 1,000, 10 to the 4, something like that. What is the usual? So we cannot say we cannot say anything more than that unless we have a model. We compare, of course, with the results of Muzzerole, and it is possible. So, but we need a better model.
Thanks.
Thanks. Our next question is from Len on Zoom.
Hi, thank you. I was wondering if you had enough photons to look at the red side, blue side visibilities and whether you saw any asymmetries there.
We have enough photons. We are lacking a little bit of spectral resolution. Yes. So with a better spectral resolution, it will be possible. Now it's hard because even if the bracket gamma line is broad, our spectral resolution is not so high. So we can try to do it with in sources with very high signal to noise, but you are always uncertain because of the small spectral resolution.
Got it. I agree. It's very exciting data and fantastic to see this gas dust. It's come a long way since the early days of the interferometry.
Yes, it is.
Oh, thanks. We also have a question from Antonella on Zoom.
It's more a comment than a question. I just wanted to follow a moment on what Michael was asking or what Nuria was saying. We really needed to have models for this inner gaseous disk because we can make this very rough estimate of the column density that you need, assuming a single temperature, by the way. But then we have no idea what is the hydrogen column density. So all you can make is a kind of plausibility argument that if you have a certain accretion rate with a certain viscosity, maybe that is not unreasonable that you have so much CO. But that's all one can do so far. So I know that Uma Gorti and David Hollenbach is working on that, and maybe Nuria will be triggered to do more work on that on those lines, because without proper models, it's very hard to say more than what Rebecca has said.
So any more questions? So maybe I can ask you a question, Rebecca?
Yes, you can.
So you said for TW Hydra that because it only has a narrow component, it has no MHD wind. So what do you think the narrow component is tracing then?
Is it tracing the photoevaporative wind, but farther away?
You think so?
So much farther away than 3.5 stellar radii. So I think there was the measurements from Ilaria, no? So the Pascucci, so something beyond 2-3 AU for sure.
Okay. Okay. Okay, so we can thank Rebecca again. Okay, so our next talk then is online, and we have Alberto Sana from INAF de Cagliari, and he's going to talk about physical conditions in the warped accretion disk of a massive star. Okay, so Alberto, when you're ready.
So welcome everyone. It's a pleasure to be here. And in the following, I'm going to talk about how the most massive stars form. And I'm going to complement somehow what Adam was talking about just a few talks before. And we show some of the most recent results that we have obtained in this field through ALMA observation at a very high angular resolution. So I'd like to start my talk with a summary of the final results and then move back to explain our measurement step by step. Here is an image of the accretion disk around our 20 solar mass young star, which is located in the star forming region called G23.01 minus 0.41. This image was obtained by ALMA with a high excitation energy line of methanol, which is indicated to the top right. And the accretion disk is presented here in the reference system of the outflow axis and the disk plane for clarity, where the white ticks are spaced by 500 AUs, each one to the other. So first, we observe disk temperatures, which increase from about 100K at 3000 AUs from the protostar to 270K at a radius of 250 AUs. And the temperature slope among these extremes goes with the radius to the minus 0.4. At the same radii, the volume density increased from a few 10 to the 7 H2 particles per cubic centimeter to several 10 to the 9 H2 particles per cubic centimeter, indicating that the inner region are really heavily opaque. At the radius of about 500 AUs, where the disk gas likely becomes centrifugally supported, we have inferred that the mass inflow rate is of about 6 times 10 to the minus 4 solar masses per year, which suggests that the star may at least double its mass at the end of the accretion phase. We also derived that the disk is prone to fragmentation, which may bring to stellar companion, if they are not already present within the disk, of course. And finally, we observe two striking spiral-like features, which we see to the northeast and southwest of the disk. And we think they are likely projection onto the plane of the sky of accretion streams, where we have detected velocity gradients of about 1 kilometer per second per 2000 AUs. So let me now make a step back and show you the environment where the disk exists and how we measured its physical properties. On scales of 10,000 of AUs, as you can see here in this plot, ALMA detects a ridge of dust emission at 860 micron, which extends in the southeast and northwest direction with the peak brightness to the northwest. The molecular line emission from species which trace densities equal or higher than 10 to the 6 per cubic centimeter is only found within a radius of about 3,000, 4,000 of AUs from the dust continuum peak. So, for instance, within this radius, native cyanide emission detected with the submillimeter array near 220 gigahertz shows a rich spectrum with several lines, which comes from the K-ladder of the 12 to 11 rotational transition. When we model the emission and relative intensity of the CH3CN lines and those of its isotope CH313CN, we infer an average temperature of 195 K, which is actually typical of a hot core. And this is a difference with what Adam was telling before for his case. So then we looked into the molecular line emission surrounding the continuum peak. And on the right side, you can appreciate the gas distribution revealed by ALMA, which shows up these two striking spiral-like features. So across the whole structure, the following pointings sample both the spiral-like features and the disk midplane. And we have used these spots to characterize the physical properties of the dense gas locally and the disk properties as a whole. So furthermore, from now on, I rotate for clarity the reference system in order to have the vertical axis of the plot aligned with the outflow axis, which falls at the position angle of minus 57 degrees. Indeed, the very large array reveals an elongated radio continuum emission at both 1 centimeter and 7 millimeters, whose spectral index indicates the existence of a radiothermal jet arising from the center of the disk. And in particular, the ALMA and VLA images prove the perpendicularity of the disk and jet directions and justify the choice of the reference system, which I will use in the following. So now moving to this most suitable reference system, I'll start to analyze the physical conditions locally. So at the loci of these various pointings that I've just shown you, we have fitted the ALMA spectra of the K-ladder of the CH3CN 19 to 18 transition and those of its isotope homologue CH330Cn, which all fall near 349 gigahertz. As an example, here are shown 3 spectra taken at the position indicated in the image, which sample the inner disk regions, the outer disk regions, and the spiral regions. So the synthesized spectra shown in red allows us to get a number of parameters, including the fluidal maximum of the lines, the gas temperature, and the column density, which are indicated on the top right of each spectral panel. And these parameters are representative of individual regions with a diameter of 500 AUs. So we have then used the measured temperature and column densities along the disk plane obtained from each spectrum to study the dependence of both quantities as functions of the radius from the young star. And the results are plotted on the right side, where the open and filled circles marks the eastern and western sides of the disk, and the red and blue dots the 2 apparent spiral regions. In particular, the fits are given as power laws of the radius from the star and are written to the right. One can also explore the suitable geometry of the disk, which is seen almost edge-on, to derive the column density values, the average volume density of the disk along the line of sight. This relation is now shown in the lower plot. From this average trend, we can also make a further step and estimate the peak volume density at the closer distance of 250 AUs in the star, which we derive to be about 5 times 10 to the 9 H2 particles per cubic centimeter. So then one may ask whether these physical properties can be used in combination with a dedicated simulation for the formation of high mass stars to gain some more insights on the nature of the central star. And indeed, the simulation by Kuiper and Ozokawa showed that the value of temperature slope as a function of the disk radius between 100 and 2000 of AUs from the star is a stable indicator of the YSO age and mass. Or the other way around, if the temperature slope is well constrained, as in our case, it is possible to reasonably estimate the age and mass of the central star indirectly. So in the right plot, it is shown the theoretical trend of the temperature slope of the disk from Kuiper and Ozokawa, with the YSO age to the bottom and the YSO mass indicated on the top axis. The comparison with our measurement, which is drawn with a dashed red line, and where the gray area gives the 1 sigma uncertainty, suggests that the YSO in G23 has an age earlier than about 40,000 years and a mass between 20 and 30 solar masses, consistent with our former estimate based on the spectral energy distribution inferred with the Herschel fluxes. But another model comparison, which is particularly useful, is that with Crater and collaborators from 2010. These authors describe the stability of a disk around a massive star undergoing rapid accretion, and is based on mainly on 2 parameters, which are 2-dimensionless accretion rates. The first one is called gamma and is a rotational parameter which relates the accretion timescale to the orbital timescale of gas around the star. Instead, the second parameter, which is called xi, is a thermal parameter which relates the mass accretion rate to the local sound speed of disk material. And the relative magnitude of gamma and xi defines the stability of the disk against local fragmentation and under rapid accretion, which is the condition that one can expect for the formation of IMAS young-star objects. So we have derived all these quantities needed to estimate gamma and psi through a direct analysis of the local spectra and a dedicated radiative transfer model for our source from Sana and collaborators in 2009. In particular, gamma depends on the mass inflow rate, which we consider a constant in time, as done in the work by Crater and collaborators, and then depends also on the mass of the system, which is given by the sum of the star mass and the disk mass at a certain radius, and also on the angular velocity of gas at the same radius. So psi instead, apart from the mass inflow rate, depends on the local temperature of gas at a given radius, which we have measured from our spectra. So now if we plug our estimates into the previous formulas, we can study the relative magnitude of gamma and psi at each position where we sample the disk and also the apparent spiral regions. So the upper and lower panels with the gamma on y-axis and psi on x-axis describe the state of the system for a sub-Keplerian and a Keplerian rotation curve. And because of our former kinematic study, we expect the system to behave in between these two extremes. And as I've anticipated, the gamma and psi defines two regions where the disk can be considered stable or fragmenting. And these regions are indicated in the plots as white and gray areas, respectively.
You have 2 minutes left.
Yeah, in these plots, each number circle indicates a position along the disk plane, and the blue and red dots instead give pointings along the apparent spiral features. So the results from this analysis are that gamma and psi couples distribute near the boundary between a stable and unstable disk, and the accretion disk meets the condition for fragmentation marginally along its wall extent. However, the snapshot taken in these panels is representative of just of a temporary solution, of course. So it does not tell anything about the evolution of the system, which we cannot predict without further information about its history, for instance, because the disk may have already developed internal fragments in the past. And for this, we need to go for continuum observations of optically thin dust emission. So let me finally summarize these results as follow. First, from the point of view of the spatial morphology, we have resolved an accretion disk which shows up with the two striking apparent spiral features, and also these features also display some asymmetries between the gas and dust components. We have then derived the dependencies with radius of the temperature, column density, and volume density along the disk midplane and apparent spiral features, and we have also found that these values, estimated values, are in excellent agreement with recent simulation models for the formation of IMAS young-star objects. So doing so, we have shown that high excitational energy transition of methyl cyanide allows us to peer into the inner disk regions. And this holds also for metal, which in particular in this case shows a standard Maser plateau within a radius of 2000 OVUs from the young star. We have then applied a new stability analysis developed by Crater and collaborators in 2010, which holds under rapid accretion, which you should expect for IMAS object. And the results of this analysis is that our disk is marginally prone to fragmentation along its wall extent. Finally, as an outlook for our work in progress, we're going to search for disk midplane disk substructures through optically thin dust emission. possibly in band 3 and 4 of ALMA. And thanks for the attention.
Thank you, Alberto. Do we have any questions? Yeah, Wingfield.
Thanks, Albert. It's very nice results. You were saying that this is an edge on disk, right? In this case, it would be possible to use a rotation curve right away to infer the central mass. So I looked up in your paper the radial velocities of the eastern and western side, and they don't seem to indicate or clearly indicate kind of rotation. So can you comment on the kinematics of the source?
Yeah, sure. Well, with previous ALMA data, we have analyzed the position velocity plots along the disk midplane as traced here. And what we have found is that for radii outer than 500 AUs, the rotation curve is a combination of subcaplarian rotation and infold, okay? And then within 500 AUs, we have instead evidence that the gas becomes centrifugally supported. So these is the are the functions that we have obtained in previous work that we have applied here. But,
okay, thanks. And do you think that the subcaplarian rotation is related to the infall?
Sorry?
Do you think that the subcaplarian rotation in the outer regions is related to the infall? So it's kind of a viscosity which is going on there.
Yeah, I would say so. I would say so. Also, the evidence we have now in these apparent spiral features that there are these gradients which goes from the tip of the spiral features, which is close to the ambient velocity, to the velocity of the outer parts of the disk. I mean, it's consistent with this view.
Okay, thanks. Very nice.
Yeah, thank you.
Okay, so we'll thank Alberto again and we'll move on. Okay, so for our final talk then we have Pauline McGuinness from DIAS, and she's going to be talking about X-shooter spectra of Upper Scorpius. Thanks, Pauline.
Thanks. So hi, everyone. For anyone who still doesn't know who I am, I'm Pauline McGuinness. I'm a postdoc here at the Dublin Institute for Advanced Studies. And I'm going to be talking a little bit about a project that's currently ongoing that I'm doing in collaboration with Antonella Nata and Carlo Manara and Miriam Benisti. And we're looking at just a few dippers in the Upper Scorpius star forming region. And Carlo will be happy to know that I don't have Lee's cartoon on my presentation, but only because I don't have time to talk about it. So. And luckily for me, dippers have already been mentioned, so maybe I don't need to explain exactly what they are. But one interesting thing about looking at dippers, or at least in Chitauri stars, the time scale of the variability that we see, it's consistent with matter in the inner part of the accretion disk occulting the star at so. The idea is that these flux dips that you see in the light curves, they're due to just matter in the inner part of the disk coming in front of our line of sight and occulting the star. And so this gives us an opportunity to study the dust in the inner part of the disk, which is still very hard to get spatial resolution to study. And so here are just a few examples. These are the 3 stars that I'm actually going to talk about. These are a few examples from these 2 papers, and these are dippers in Upper Scorpius. And so there have been a few mechanisms proposed to lift dust off of the disk midplane so that dust can get in front of our line of sight. And one of those Sylvia has already mentioned today, which is the accretion-driven disk warp. So you have dust being lifted at the base of the accretion columns because of the interaction with the magnetosphere of the star. And you can have other types of warps in the disk as well because of maybe instabilities or possibly because of planets. And there's also been proposed, it's also been proposed that disk winds might be able to lift a certain amount of dust from the disk midplane, and that dust would come in front of our line of sight. So as has also already been mentioned, these require a certain inclination, a certain viewing angle for us to be able to observe these dippers. And well, it's been observed that at least a few of these dippers, they don't have, at least the images of the outer disk of these systems show that the outer disk is very much not close to edge on. So this is a very, very beautiful example of this particular star here that we call J1604 for short. And just because no one wants to remember a whole 2-mass number. And this is from Ansdell and collaborators 2020. And so you see this is the ALMA image, and you see this beautiful ring, and it's clearly seen close to face on. And it has a very large gap in the middle, a dust gap in the middle part of it. And it has a very, very typical dipper light curve. It's very hard to explain this behavior with something like spots, with something that isn't dust occulting the star. You know, you have sometimes dips of 70% of the flux of the star. And so what's been proposed, not just because of the light curve, but also because of these shadows that you see in sphere images of this system. What's been proposed is that there is this huge misinclination between the inner part of the disk, which would be all the way in the middle, a tiny little part in the middle there that's completely misaligned with the outer part of the disk. And so this is a very interesting system to study, and we wanted to study actually a few dippers. And so for now, I'm going to, well, the immediate goal of this particular study was to look at a few dippers and try to understand a bit more about the properties of the dust in the inner disk that are causing these occultations. And this is actually part of a larger study that we're getting observations for. And the idea is to try to get a statistically significant sample of dippers, not just in Upper Scorpius, but in several star-forming regions, to try to study better the properties of the dust grains that cause these occultations, but also ultimately we would also like to try to understand better what is the main mechanism that's there to lift the dust off the disk midplane, if there's one main mechanism, or if maybe different systems have different mechanisms at work. So today I'm going to be talking really more just about the dust. So like I said, these are the 3 systems that we looked at. And so this one in the middle is J1604. It's a K2 type star of 1.13 solar mass. And we also have, so I should have mentioned, these are K2 light curves. This one on top was actually observed twice by K2. So you can see in black and in gray are 2 different observations. And in gray in particular, you see this large dip here. And so this is a K0 type star, which we call J1558 for short, but it's also HD 143006 of about 1.5 solar mass. And then we have a cooler star that we call J1602, which is an M0 type star of about 0.4 solar mass. And you can see that they're pretty low accretors. These 2 in particular, J1604 does have some fairly broad profiles. So we see that there is a bit of accretion there, but it's clearly very low. J1602 actually has very narrow profiles. It would be classified as a weak line Chitauri star. So this mass accretion rate is probably not real. It's probably just from the chromospheric emission that this was measured. And so we observed these systems with X-Shooter, and we got 3 epochs of X-Shooter and X-Shooter spectroscopy. And the advantage of X-Shooter is that you have this huge wavelength range from the ultraviolet to the near infrared. And at the same time, you also get lots of emission lines that come from the accretion and the ejection processes in these systems. And you get that simultaneously, and because it's flux calibrated, you can see how all of that changes with the flux dips. And it has a pretty decent resolution, especially in the optical. So we can see also the shape of those line profiles. Unfortunately, I don't have time to talk much about the line profiles now. So we focused a bit more right now on the shape of the SED. And what I did was, because I wanted to kind of just see how the continuum varied in these 3 different epochs, I used like a sigma clipping filter to get rid of the emission lines and the deep absorption lines, just smoothed out the continuum. And these are 3 random epochs. They weren't observed like one day after another or something like that. But even though they were random, we did manage to get some pretty nice dips. So for this star, for instance, we get one dip of about 55% in flux in the optical and 63% the other dip. And this one, 2 of the observations were at the maximum, but we got at least also 1 dip. And here again, we managed to get a dip. So you can see that the shape of the SED also varies a bit with the dips. So one thing that we did was we fitted the SED with a template, class 1 weak line T-Tauri star template of the same spectral type, plus a black body emission of temperature 1500 Kelvin. And that would just be the temperature of the dust in the inner disk. And the first thing we note is that you need a pretty high luminosity of that black body there. And this can't really be accounted for with a very flat inner disk. You need more area. You need something like either a puffed up inner rim or maybe an inner disk warp to have that much emission. But the most notable thing is that when we take the dimmest epoch and we divide it by the brightest epoch, and we see that there is a very flat relation there. So these dips occur in a way that's very wavelength independent. And so that cannot be explained by something like extinction from interstellar medium, because that would give us a slope that would look like this, this line here. And so in order to explain this flat extinction curve, taking in some fairly simple assumptions about the dust, we find that you need a grain distribution that includes some very large grains up to about 150 micron in size. And so for this particular star, as you maybe noticed here, the middle observation actually seems to behave differently. And you might think that, well, this middle one could maybe be explained by interstellar extinction or something like that. But we see that it looks more like enhanced emission in the infrared, actually. So that's this one over here. And you can actually reproduce this SED with the same template scaled in a wavelength independent way for the dip, plus enhanced near infrared emission here. So this is probably pointing to some sort of inhomogeneity in the inner disk that's causing this near infrared excess, which could potentially be, for instance, because of a warp. And so that was J1558. J1602, which is the much cooler star, it doesn't have a lot of infrared excess. It has very little infrared excess, which is also consistent with the very little amount of accretion or possibly no accretion that we measure, but it also shows that flat relation during the dip. So you also need some pretty large grains to reproduce this. J1604, on the other hand, which is that beautiful system with the ring and the misinclined inner disk potentially, this actually doesn't have a very flat extinction curve, but it's also not quite consistent with the interstellar medium, but you can reproduce this with grain distribution, taking fairly small grains into consideration, so up to about 3 microns. So you also see a bit of enhanced emission during the dips, like we did with J1558. And so basically you see that this system in particular, it's a bit different than the other dippers. And we do need to study a larger sample of dippers to see what is really the typical behavior. But we can say that the dust that is occulting this star in particular, it's not quite as processed as the one in the other 2 stars. So yeah, these are my main conclusions, basically that for 2 of the stars in our sample, the occultations are consistent with a wavelength independent extinction curve. And we really need grain distributions, including very large grains, to explain that. Whereas for J1604, you can explain its behavior with smaller grains. And for at least one of the stars, we see an increase in the near infrared excess during the occultation. And this excess corresponds to a considerable fraction of the stellar luminosity. Thank you.
So we have a question from Nuria.
Yeah, very interested. If you were to interpret the emission, that excess emission, like from the rim, the inner rim, how many scale heights would you need?
Oh, I don't know. We haven't calculated that yet.
Mm-hmm. And the other question I had is like for the M0 star, have you looked at the 10830 line and see if it has redshifter absorption? Because even like for very low M dots, you can see if sometimes like the redshifter absorption, even for 10 to minus 10, indicating there is a peak.
I'm trying to remember what that profile looks like. I have looked at it a few times, but I don't remember. I'll look into that. Thanks.
Okay, Bill? Question?
Hi, yeah, it was a nice talk. I don't know very much about dippers, but kind of what I know from the past about when people talk about grain sizes is they often talk about gray extinction, and then it's quite often it's suggested as a possibility to explain data, and then it's quite hard to find a case where it stood up to the test of time. Now, I think you might actually have a real, I'm not saying I disbelieve you, I think you might actually have convincing results here. And what the classical idea is that the large grains are hidden in the midplane of a disk. So are you suggesting that maybe these grains are so close to the star that this is the part of the disk that's basically been, there is no midplane, there is no organized disk because it's too close to the star, and so the stuff is floating close to the star that would normally be hidden in the midplane?
Well, not necessarily, because in order to see the dips, that dust has to cross your line of sight. So it can't be just on the midplane, because if you're seeing it edge on, then you wouldn't even be seeing the star. It needs to be, it can be at a high inclination, but not quite edge on.
Yes, I'm saying stuff that's normally, it's stuff that's normally hidden in the midplane, but for some reason is it stuff that's sufficiently close to the star that it's levitated above the midplane?
Yeah, it has to be lifted above the midplane somehow. And there are a few attempts to explain how that dust is lifted from above the midplane. So there are models that show that disk winds might be able to carry some dust, but I don't know what the limitations are on the size of that dust. And there's also the idea of the inner disk warp caused by the interaction with the magnetosphere of the star. So if you have dust at the truncation radius, then you have dust also being lifted at the base of the accretion columns. And that's the idea that was proposed for AA Tauri, for instance, and that we've seen a few other stars that seem to, potentially fit that scenario.
So we have a few questions on Zoom. The first one is from Jerome.
Yes, hi, Pauline. I was wondering whether you consider scattered light in your model, because when you are in a deep, you depress the photospheric photospheric light essentially, and then depending on the geometry and the inclination of the system and so on, you might start to be dominated, at least in the blue range, by the scattered light, and maybe that's the origin of the blue bump that you see in your model for J1604, for instance.
Okay. So Antonella did these calculations, and I'm almost certain that she included absorption and scattering in them. I don't know if she's raised her hand to say something, but I'm pretty sure it's okay. So I think it was taken into consideration, yes. And Antonella can correct me if I'm wrong.
May I say something?
Go ahead.
Yes, but there's no geometry in it. I just try to mix things with a ratio, with a different, with the ratio scattering versus absorption, that to see if I could reach some result that would look interesting, and I couldn't. One of the things that I keep thinking is that if we have a very optically thick something that covers just a fraction of the emitting region, then we will have the same effect of a gray extinction. Which will then tell nothing about the kind of grain size that one has, which on the other hand, as you know, it depends on so many assumptions that I am always, not very happy to quote numbers. But so, I mean, scattering is a problem. It depends on details. I try to see how, the effective albedo that one needs, and I couldn't find anything that was particularly, that would allow me to fit things with very small grains. But it's just a kind of experiment. It's not very serious. And the idea of a very optically thick, small region, I think is fascinating, but I don't know what it could mean. I cannot put, one should be able to put some limits on that, but then it depends on the inclination more. And if everything is misinclined, etc., then we know nothing about it. So I don't know.
I think also if you take something that's completely optically thick like that, the problem is, in order to get these flux dips of, taking away 60–70% of the flux of the star, they need to be very big, right?
They have to be very big anyway.
Yeah.
Yeah. Even, yes. So.
Okay, thanks, Antonella. I actually have a short question before we head off. Actually, in that plot that you have there, the extinction curve, I may just be over-interpreting it, but it seems like they all had a bit of a bump in kind of the center point, all of the extinction. Is that just an error, like within the error?
I think it's all, I forgot to plot error bars. I think that's all within the error bars.
Because it just seemed to be at a similar place in each of your stars, so I was curious. But
it might be where there's a telluric absorption region and there was a bit of a bump.
Just curious.
I think it's within the error bars. Yeah.
Okay, so I think we can finish there, and we'll thank Pauline and all the speakers.
Thank you.